The electron builds atoms, sparks light, and makes life possible, but the universe didn't stop at one. It quietly forged two heavier copies, the Muon and the Tau, and three ghost-like neutrinos that slip through Earth like we aren't here. Why does reality repeat this pattern 3 times? And what are these strange echoes really pointing to? New physics, a crack in the standard model, or the missing clue to why matter won at all? In the particle ledger of reality, there is a repetition so exact it feels intentional, and so unexplained it feels dangerous. 3 times nature writes the same lepton script, then changes only the mass and the clock. In laboratories, we do not meet these particles as characters, we meet them as traces. A spiral in a magnetic field, a flash in liquid, a delayed pulse in a detector wall, and yet those traces keep balancing, as if the universe is keeping accounts with obsessive precision. Charge conserved, spin tallied, interactions following rules we can write down but cannot justify. The standard model is our best rulebook for that accounting, and it is almost offensively successful. It predicts what colliders will produce, how atoms will shine, how forces trade particles like currency, but it also carries a quiet, unresolved pattern, one that survives every cross-check, every null result, every upgrade in precision. The lepton families line up in 3 columns, identical in their gauge charges, and wildly unequal in mass. That inequality is not a footnote, it is the plot. Mass determines which particles live long enough to matter, which decays are allowed, and which quantum loops can whisper about new physics. Follow the Muon and you find a particle that acts familiar while it probes the world at shorter distances. Follow the Tau and you find a 3rd generation that barely exists, yet leaves signatures sharp enough to reconstruct from debris. Then come the neutrinos, so aloof that we infer their presence from missing energy and impossible transformations. They are born in flavors, travel as mixtures, and return wearing different names, as if identity itself is negotiable. This is where the story stops being a catalogue and becomes an investigation. Why would nature repeat a lepton 3 times, then hide the reason inside masses we cannot derive? We will step into the standard model's architecture, its symmetries, its fields, its elegant constraints, and watch where the elegance ends. We will see how universality is tested in rare decays, and why small deviations matter more than dramatic ones. We will follow precision to the edge, where a muon's magnetic wobble becomes a referendum on vacuum fluctuations. There, the numbers are so tight that even a subtle mismatch can imply new particles passing through the calculation unseen. And we will widen the frame beyond accelerators, because the early universe kept its own records. Neutrinos helped set the tempo of expansion, shaped what could clump into galaxies, and may still carry a hidden asymmetry that echoes the oldest question of all. Somewhere inside this 3-generation pattern, there may be a clue about the origin of mass, the fate of lepton number, and the reason the cosmos contains more matter than antimatter. For now, we have repetition, we have precision, and we have an absence of explanation, an invitation to look closer. So we begin with what seems ordinary, the electron's role in stable matter, and the first hints that ordinary is a special case of something deeper. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey, from everyday electrons to cosmic ray intruders, from fleeting taus to shape-shifting neutrinos, each chapter tightens the same question. By the end, the threefold pattern will feel less like redundancy, and more like a map whose final landmark remains just out of sight. The electron feels ordinary because it is everywhere, binding atoms, carrying current, and making chemistry possible. In a simple picture, it sits in a cloud around the nucleus, and its negative charge is pulled inward by positive protons. Quantum mechanics refines that picture, because the electron is not a tiny planet, and its orbit is not a path. Instead, it occupies a probability distribution, an orbital, whose shape determines how atoms bond and how materials behave. That negative charge locks the electron to the positive nucleus, and that balance makes stable matter. If the electron were much heavier, its orbitals would shrink, and chemistry would look unfamiliar. If it were much lighter, atoms would be puffier, and the periodic table would reorganize itself. Every solid object, every wire, every screen, and every nerve signal depends on electrons behaving predictably. Even the colours we see are electron transitions, tiny energy steps that become photons and then become vision. In the particle zoo, the electron looks like the dependable baseline, the unit we build intuition around. It is also one of the best tested objects in science, because its charge and magnetic properties can be measured with extraordinary precision. In laboratories, electrons spiral in magnetic fields, and their trajectories draw clean arcs across detector screens. In the everyday world, the same rules quietly govern a phone's circuits and a lightning bolt's branching path. Yet the electron is also a clue that nature repeats itself in a way we cannot justify. In the mid-20th century, experiments studying cosmic rays found tracks that did not match any known particle. In cloud chambers, thin vapor trails curled through magnetic fields, and some curves suggested a particle like the electron, but stubbornly heavier. It had the same charge and the same spin, and it interacted through the same forces, but it was heavier, and it did not belong in ordinary atoms for long. That particle was the muon, and it arrived like an unwanted duplicate. Physicists famously asked, in effect, who ordered that, because the discovery felt like a redundancy rather than a necessity. The muon did not solve an immediate problem in chemistry or nuclear structure, and it did not fill an obvious gap. It simply existed, as if the universe had printed a second copy of a familiar page. The muon is not a composite object, not an excited electron, and not a temporary bound state. It is a fundamental lepton, point-like as far as we can tell, with a mass about 200 times larger. That mass has consequences because heavier particles respond differently to forces at short distances. A muon lives only microseconds before it decays, usually into an electron and neutrinos, and the decay is governed by the weak interaction. If a muon is slowed down inside matter, it can replace an electron in an atom briefly, shrinking the orbit and amplifying quantum effects. The muon's tighter orbit drags it close to the nucleus, where the finite size of the proton and the details of nuclear charge distribution matter. Spectroscopy of these monic atoms becomes a microscope for nuclear structure, because the muon samples regions an electron rarely reaches. But the muon does not build the everyday world, and that is the first discomfort. Why does nature make a heavier copy of something it already has? Then the pattern repeats again, even more dramatically. The tau lepton appears as a third charged lepton, again with the same charge and spin. It is far heavier than the muon, and it decays even faster in a tiny fraction of a microsecond. Its decay products can include hadrons because the tau's mass is high enough to create quark-antiquark pairs. Like the muon, it does not form stable matter, and it vanishes into lighter particles. The electron, muon, and tau look like three versions of one idea, separated mainly by mass and lifetime. They share the same electric charge, the same spin, and the same pattern of electroweak interactions. What changes is how long they persist and what decays are kinematically allowed. In a detector, that difference becomes visual. An electron showers quickly, a muon punches through layers, and a tau leaves a short, subtle signature before it disappears. This is where the documentary begins, with a familiar particle and an unfamiliar redundancy. The electron is essential, but the muon and tau seem optional, like extra keys that open the same lock. Physicists call them a family, or generations of leptons, because they share the same quantum numbers. The standard model places them in parallel columns, as if the universe filled out a template 3 times. The map works, but the reason for the repetition is missing. The standard model is our best compact description of known particle physics. It organizes matter particles into quarks and leptons, and it describes forces through gauge fields. Those gauge fields are not just bookkeeping, because they encode symmetries that dictate what interactions can occur. It predicts scattering rates, decay patterns, and quantum corrections with astonishing precision. It explains why electrons repel each other, why photons mediate electromagnetism, and why weak interactions can change particle identities. It is not a guess, but a tested framework that survives brutal experimental scrutiny. Its predictions match collider data, atomic measurements, and precision tests of quantum electrodynamics. When theory and experiment disagree, the first assumption is often that the measurement is wrong, or the calculation is incomplete because the model has earned that trust. But a model can be successful and still incomplete, especially if it cannot explain its own internal patterns. Still, the standard model reads like a catalogue without a backstory. It lists 3 generations of quarks and 3 generations of leptons, then stops. It does not tell us why there are exactly 3, or why the masses span such a huge range. It does not explain why the electron is light enough to make chemistry, while the tau is heavy enough to decay into hadrons. It does not explain why the pattern is so clean, yet so arbitrary. The charged leptons are only half the cast, because each one comes with a neutrino partner. The electron neutrino, muon neutrino, and tau neutrino carry no electric charge and interact extremely weakly. They stream through Earth, through detectors, and through our bodies with almost no effect. A neutrino can cross a light year of lead without noticing, and that is not poetry, but a consequence of how rarely it interacts. In the Standard Model's original form, neutrinos were treated as massless, which made them even more ghost-like. Massless neutrinos fit neatly into the equations, and they simplified the story of lepton families. But neutrinos refuse to stay simple, and their behaviour will become one of our central clues. Their very elusiveness becomes a feature, because it lets them carry information from places other particles cannot escape. To keep the story accessible, we need a few organising rules that physicists use. Leptons are fermions with spin 1/2, and they do not feel the strong force. Charged leptons feel electromagnetism and the weak force, while neutrinos feel only the weak force and gravity. In practice, that means electrons leave tracks and deposit energy, while neutrinos mostly slip away, taking momentum and mystery with them. In many reactions, a bookkeeping quantity called lepton number appears to be conserved. An electron and an electron neutrino count as electron flavour, while muon and tau flavours have their own counts. These flavour labels are not visible like colour or charge, but they show up in what decays happen and what decays do not. They are the quiet rules that keep particle reactions from becoming a free-for-all. In quantum field theory, these numbers guide which interactions are allowed and which are forbidden. A muon can decay into an electron only if the neutrinos balance the lepton flavours. A tau can decay into a muon or an electron, again with neutrinos carrying away the missing flavour. This structure makes the generations look like separate lanes, even when particles transform. It also hints that the lanes might not be fundamental, which is exactly what neutrinos later reveal. At first glance, the generations seem like a harmless duplication. If muons and taus decay quickly, maybe they are just rare byproducts of high-energy collisions. But the universe was once hot enough that these particles were common. In the early universe, temperatures were so high that energy routinely became mass, and particle-antiparticle pairs formed and vanished in equilibrium. Muons and taus could be produced in abundance, and their decays could affect the balance of particles and radiation. The copies are not merely laboratory curiosities, because the cosmos once ran on their physics. As the universe expanded, it cooled, and reaction rates fell behind the expansion rate. When that happened, certain species froze out, leaving relic populations or leaving imprints on what came next. Even short-lived particles can matter, because their decays heat some components of the cosmic soup more than others. The details become subtle, yet subtle effects are exactly where modern cosmology now has leverage. Neutrinos push the cosmological connection even further. They decouple early, they carry energy across vast distances, and they influence how structures grow. The number of neutrino species affects the expansion rate of the universe during key epochs, including the formation of light elements. Their tiny masses, though small, shape the formation of galaxies by smoothing density fluctuations, because fast-moving neutrinos resist clumping. When we ask why there are 3 generations, we're also asking why the universe cooled the way it did. Particle physics and cosmology share the same accounting. A change in the particle roster changes the energy density, and energy density changes the expansion history. That expansion history, in turn, affects what the cosmic microwave background looks like today. So a question that begins inside an atom can end up written across the sky, faintly but measurably. It is a reminder that fundamental does not mean small, because fundamental rules scale up. So the mystery has 2 faces. In accelerators, we see redundant families that differ mainly by mass. In the sky, we see relic effects that depend on how many light particles existed and how they behaved. If the standard model cannot explain the pattern, then the pattern might be a signpost to deeper laws. It could point to hidden symmetries, new forces, or new particles that connect the generations. It could also connect to the biggest imbalance we know, the dominance of matter over antimatter. The visible universe is made of matter. Yet our best equations suggest matter and antimatter should have been created in nearly equal amounts. Something tipped the balance, and whatever did it left only a trace in today's physics. The lepton sector, especially neutrinos, is one of the few places where newer symmetries could still be hiding. The documentary's central question is simple to state and hard to answer. Why does the universe contain 3 generations of leptons, with the same charges and spins but wildly different masses? Why do neutrinos come in 3 flavors, and why do they mix as they travel? Why does the standard model classify these particles so neatly, yet leave their origin unexplained? If the universe is repeating itself, what is it trying to tell us? To investigate, we need places where nature's extremes can be recreated. Particle accelerators act like controlled echoes of the early universe, smashing beams together to produce heavy, short-lived particles. The visuals are almost architectural: kilometers of tunnel, superconducting magnets, and beams guided to collide within fractions of a millimeter. Facilities like CERN, Fermilab, and KEK do not just find new objects, they measure tiny deviations from predictions. Detectors track decay products, reconstruct energies, and test symmetries that might otherwise be invisible. Layer by layer, they separate photons from electrons, electrons from muons, and muons from hadrons. The data arrive as bursts of electronic signals, then become coloured tracks and statistical plots, and finally become claims about reality. In these machines, muons and tau stop being rare curiosities and become precision tools. Muons are especially useful because they are heavy enough to amplify subtle quantum effects. In quantum field theory, empty space is not empty, because virtual particles flicker in and out. Those fluctuations slightly shift measurable properties, like a particle's magnetic moment, and the shifts can be calculated as a series of quantum corrections. The muon's magnetic moment is sensitive to heavier virtual particles than the electron's is. That sensitivity turns the muon into a probe for physics that might be beyond the standard model. This brings us to the first anomaly that sets the tone for the series. The muon G-2 measurement compares the muon's actual magnetic behavior to the standard model prediction. The G factor links spin to magnetism, and the -2 highlights the tiny deviation from a simple Dirac particle. Experiments have reported a persistent tension, a small but intriguing mismatch. The discrepancy could shrink with improved calculations and data, or it could grow into a clear signal. If it is real, it suggests that unknown particles or forces are nudging the muon. It would mean that the vacuum is busier than we thought, with additional quantum contributions that the standard model does not include. In that case, the muon is not merely a heavier electron, but a sensor tuned to hidden mass scales. The question becomes immediate. Why does the sensor exist at all, and what is it sensing? The second anomaly is already a confirmed fact, and it directly attacks the standard model's original assumptions. Neutrino oscillation means a neutrino created with one flavor can later be detected as another. The effect is quantum interference on a cosmic scale, because neutrinos propagate as mixtures of mass states. This requires neutrinos to have mass and to mix, which the simplest standard model did not allow. Oscillation tells us that lepton flavor numbers are not absolute, at least for neutrinos. It also implies new parameters, new phases, and possibly new sources of asymmetry. The mixing angles can be measured, and the mass differences can be inferred, but the absolute masses remain elusive. There may also be CP-violating phases in the neutrino sector, and those phases could matter for the history of the universe. A particle that barely interacts can still reshape the story, simply by being slightly different than expected. Together, G-2 and oscillation form a narrative tension. One is a precision crack that might widen into new physics. The other is a proven gap that demands an extension of the model. Both point toward the same unsettling idea, that the lepton generations are not just repeated entries. They might be shadows of a deeper structure that we have not yet mapped. Before we chase explanations, we need to be clear about what the standard model actually claims. It says the electron, muon, and tau have identical electroweak charges, so they couple to photons and W and Z bosons in the same way. This principle is called lepton universality, and it is tested in many decays. Differences in behavior should come only from mass and available energy, not from different fundamental couplings. If universality fails, the generations are not true copies. A small deviation would imply that new interactions distinguish between flavors, even though the standard model does not. That would be a profound clue. Because it would tell us the template is imperfect and the repetition is only superficial, the search becomes a careful audit, checking whether nature treats each lepton with the same rules or merely similar ones. The standard model also says that masses come from the Higgs field through Yukawa couplings. Those couplings are numbers we measure, not numbers the theory predicts, and they function like dials set from the outside. The electron's coupling is tiny, the tau's is much larger, and the pattern looks unexplained. Quarks show a similar hierarchy, which hints at a shared mechanism. But the model does not tell us why the couplings take the values they do. The hierarchy is written into the theory by hand. That is why the repetition matters, even if it seems like bookkeeping. A theory that cannot explain its own family structure feels incomplete, because it cannot explain why its ingredients come in threes. The three-generation pattern is not a small detail, because it shapes which particles exist, which decays happen, and which symmetries are possible. It also constrains the early universe, where every species contributes to energy density and reaction rates. If there were more generations, the cosmos would have cooled differently, and the cosmic microwave background would carry that difference. If there were fewer, chemistry might not exist, because atomic structure depends sensitively on the electron's properties. The fact that we can even ask these questions depends on a particular arrangement of masses and charges, so the pattern is not just aesthetic, it is existential. We also cannot ignore the link to matter and antimatter. The standard model contains sources of CP violation, but they appear too small to explain the observed dominance of matter. Leptons might hold additional CP violating phases, especially in the neutrino sector. If neutrinos have special properties, they could help generate the matter asymmetry through mechanisms like leptogenesis. The generations might be part of the reason anything exists to observe. For now, Chapter 1 ends with the simplest unsettling fact. The electron is the foundation of the visible world, yet it comes with heavier siblings that seem unnecessary. The standard model describes them perfectly, then falls silent on why they exist at all. The early universe made these particles naturally, and today's accelerators remake them on demand. If we want answers, we have to follow the model's classification of leptons and then track the places where it breaks. Next, we step inside the standard model's lepton framework, and we ask what it means to call these particles copies. We follow how generations are defined, how universality is tested, and how neutrinos blur the boundaries. We treat accelerators as time machines, and we treat anomalies as clues rather than noise. The repetition is real, and the explanation is not. That gap is where the hunt begins. Chapter 1 left us with a clean duplication and no motive, like a signature repeated 3 times without an author. The electron anchors ordinary matter, yet muon and tau mirror it, then vanish from daily experience almost as quickly as they appear. Chapter 2 steps into the standard model's ledger, where the repetition becomes official. The standard model is not a story about tiny balls bouncing through empty space, even if our diagrams sometimes tempt us to think that way. It is a rulebook built from quantum fields and symmetries, tested against scattering angles, decay products, and precision measurements that accumulate like forensic evidence. In this framework, particle is shorthand for a field behaving in a particular, quantized way, and the rules are written in mathematics that enforces consistency. Visually, imagine a clean, dark grid hovering in a void, with columns labelled by forces and rows labelled by matter. Each cell is a field, not a bead, and the grid is held together by symmetry principles that act like accounting constraints. When experiments collide particles at high energy, the debris is not random. It is the ledger being audited in real time. At its core, the standard model is a gauge theory, meaning it is built around local symmetries that dictate which interactions are allowed. Those symmetries are not decorative, because they determine the very existence of force carriers and the pattern of charges. The electroweak theory unifies electromagnetism and the weak force at high energies, then splits them as the universe cools and the Higgs field reshapes the vacuum. Quantum chromodynamics governs the strong force, and it does so with a kind of relentless confinement that hides quarks inside composite particles. The standard model sorts the known fundamental fields into matter fields, force fields, and the Higgs field that changes what empty space means. Matter fields are the ones that can build stable structures, at least indirectly, while force fields mediate interactions between them. The Higgs field is different again, because it is a background that fills the vacuum and alters how other fields propagate. Matter fields come in two families, leptons and quarks, and the distinction is not cosmetic. Leptons do not feel the strong force, so they avoid the binding that makes protons, neutrons, and nuclei. Quarks do feel the strong force, so they are never seen alone in ordinary detectors, only as bound states called hadrons. That confinement is not merely experimental inconvenience, it is a fundamental feature of the strong interactions mathematics. The gluon field carries color charge, and gluons interact with each other, which makes the force grow stronger as quarks are pulled apart. The result is a kind of elastic tension in the field, so energy piles up until it becomes new quark-antiquark pairs. In practice, trying to isolate a quark produces a spray of hadrons instead, an unmistakable signature in collider images. Force carriers are also fields with their own quanta, and the standard model treats them as essential bookkeeping entries. The photon carries electromagnetism, the gluons carry the strong force, and the W and Z bosons carry the weak force. These bosons are not optional messengers, because gauge symmetry demands their presence once the charges and symmetries are specified. The weak bosons are heavy, and that heaviness is why the weak force is short-ranged in everyday life. A heavy mediator makes an interaction fade quickly with distance, so weak processes are rare at low energies. Yet in high-energy collisions, W and Z bosons appear as real particles, leaving crisp experimental patterns in their decay products. Their masses are also a clue that the electroweak symmetry is hidden rather than absent. Gravity is not included in this framework, which is an early sign that the model is not the final layer. The standard model is quantum, while gravity is still described by classical space-time geometry and general relativity. That mismatch becomes unavoidable at extreme energies, where both quantum effects and space-time curvature should matter. Even here, in a chapter about leptons, the missing gravity entry is a reminder that the ledger is powerful but incomplete. The Higgs field is the model's mass mechanism, not a simple add-on that can be removed without consequences. It has a non-zero value even in empty space, and that background changes how particles move through the vacuum. In plain terms, the vacuum is not nothing. It is a medium with structure, and fields respond to it. When the Higgs field takes on its vacuum value, it breaks the electroweak symmetry in a controlled way. The photon remains massless, preserving long-range electromagnetism, while the W and Z bosons acquire mass. This symmetry breaking is not like shattering a crystal, but it is like choosing a direction in an abstract space of possibilities. The choice locks in the pattern of masses and interactions we measure. Some particles couple strongly to the Higgs field and become heavy, while others couple weakly and remain light. The coupling strength is encoded in parameters called Yukawa couplings, and each fermion has its own. The standard model can tell us what happens once those couplings are specified, but it does not tell us why the couplings take their particular values. This is the first place where the ledger looks more like a record than an explanation. The standard model's most striking organizational choice is generations, because it takes a set of matter fields and repeats it. A generation is a repeated template of matter fields, with the same gauge charges, but different masses. The interactions are copied, the quantum numbers match, and only the mass parameters shift. It is hard not to notice how deliberate that looks when it is written as a table. In one row, an electron sits beside its neutrino. In another, a muon sits beside its neutrino. In a third, a tau sits beside its neutrino. The charges line up like duplicated forms, and the forces treat each form as valid. The question is not whether the pattern exists because it is right there, but why nature chose to repeat it. For leptons, each generation contains a charged lepton and a neutrino partner, linked by the weak interaction. The first family is the electron and the electron neutrino, the pair most familiar because electrons shape chemistry and electricity. The second family is the muon and the muon neutrino, which appear in cosmic ray showers and accelerator beams, then decay away. The third family is the tau and the tau neutrino, heavier still, produced in high-energy environments and gone almost instantly. The third family is the tau and the tau neutrino, and the tau's short lifetime makes it feel like a visitor rather than a resident. These pairs share the same weak structure, because they form the same kind of electroweak doublet. That is the template nature repeats 3 times with no explanation attached, as if the ledger lists 3 copies and refuses to add a footnote. In the electroweak theory, left-handed charged leptons and left-handed neutrinos are paired into doublets, while right-handed charged leptons appear as singlets. This chiral structure matters, because the weak force only couples directly to left-handed particles and right-handed antiparticles. The The standard model is therefore not symmetric between left and right in the way everyday intuition might expect. That asymmetry is built into the ledger's rules, and it shapes every decay we observe. The charged leptons all carry electric charge -1, and that sameness is one of the most rigid facts in the table. They all have spin 1/2, and they all couple to photons in the same way, which is why they all respond to electric and magnetic fields. They also couple to the W and Z bosons with the same electroweak charges, so the weak force recognizes them as the same kind of object. If you ignore mass, the forces cannot tell an electron from a muon. Neutrinos carry no electric charge, so they ignore electromagnetism and pass through matter with eerie ease. They still couple to the weak force through the W and Z bosons, and they still respond to gravity, but weak interactions are faint and rare. In the original standard model, neutrinos were treated as massless, which made the family pattern look even cleaner. That choice was not arbitrary at the time, because experiments had not yet forced a different conclusion. Quantum field theory reframes what a particle is, and it does so in a way that makes the repetition more puzzling. A particle is an excitation of a field, a quantized ripple that can be created and destroyed. There is an electron field, a muon field, and a tau field, each filling all of space, even when no electron, muon, or tau is present. Picture a calm, dark ocean that extends everywhere. Then imagine a localized ripple that travels, scatters, and can disappear. That ripple is what we call a particle, and the ocean is the underlying field. In a detector, we do not see the field directly, but we see its excitations as tracks, flashes, and energy deposits. The ledger is written in those traces, translated from the language of fields into the language of instruments. This is where the strangeness sharpens, because the electron, muon, and tau fields have identical gauge charges. The forces see them as the same kind of object, so their interactions are copies of one another. Yet the fields are distinct, and their excitations carry wildly different masses, which means they respond differently to acceleration and decay. The duplication is not a minor echo, it is a full repetition with a dramatic rescaling. In the standard model, those masses come from Yukawa couplings to the Higgs field, which act like adjustable knobs. The Higgs gives a universal mechanism, but it does not give universal numbers. Each lepton has its own Yukawa coupling, and the theory does not predict their values. We measure them, we insert them, and the ledger balances. The Yukawa coupling is, in effect, a measure of how strongly a given fermion field feels the Higgs background. A larger coupling means the field's excitation behaves as if it carries more inertia, which we interpret as greater mass. That statement is precise in the equations, yet it still leaves a human question unanswered. Why should the electron's coupling be tiny while the tau's is comparatively large? So the model can compute how a given mass behaves, but it cannot compute why that mass exists in the first place. It can predict decay rates once couplings are measured, but it cannot derive the couplings from deeper principles. The ledger balances perfectly, yet the entries look chosen, not explained. Even the elegance begins to feel like a clue. The mass hierarchy is not subtle, and the numbers are too large to dismiss as rounding errors. The muon mass is about 207 times the electron mass, which means a muon is the same particle in charge and spin but vastly heavier in inertia. The tau mass is about 3,477 times the electron mass, pushing it into a regime where many decay channels open. These ratios are so stark that they read like a deliberate pattern, yet the standard model offers no reason for the spacing. To make those numbers concrete, recall that the electron's mass is about 0.511 MeV, a unit tied to energy by Einstein's relation. The muon sits at about 105.7 MeV, heavy enough that it can be produced in cosmic ray collisions high in the atmosphere. The tau rises to about 1.777 GeV, heavy enough that it requires powerful accelerators or extreme astrophysical events to appear. The same template spans 3 very different energy scales. These are not small corrections to a baseline, because they change lifetimes, decay channels, and how deeply a lepton probes quantum fluctuations. A heavier lepton can couple to more possible final states, simply because energy conservation allows more combinations. It also samples shorter distances in quantum loops, which makes it a sensitive probe of subtle effects. But none of this changes the lepton's electric charge, its spin, or its basic electro-weak identity. The lifetimes make the contrast vivid in the lab. The electron is stable, at least as far as any experiment has ever seen, so it persists as a building block of matter. The muon lives for about 2.2 microseconds before decaying, long enough to leave a track through a detector and even penetrate deep into rock. The tau lives for only about 0.3 picoseconds, so it decays almost at the point of creation, leaving only a tiny displaced vertex as evidence. Neutrino masses sit in a different regime, and their smallness is part of the mystery rather than a relief. They are tiny compared to the charged leptons, and for a long time they were consistent with zero in experiments. Oscillation data now demands non-zero masses, yet the standard model still does not predict their scale. The ledger, which is so precise elsewhere, leaves this line item incomplete. The result is an uncomfortable split that sits right inside the lepton family pattern. Charged leptons look like copies separated by Higgs couplings we cannot explain. Neutrinos look like ghosts with masses that require new ingredients, or at least new terms beyond the simplest model. The same family template contains both the most familiar particle in daily life and the most elusive particle in the cosmos. Lepton universality is the principle that the weak force treats electron, muon and tau identically, aside from effects caused by their different masses. In practice, it means their couplings to W and Z bosons are the same, because the gauge charges are the same. Any difference in decay rates should come from mass effects and available phase space, not from a hidden preference in the force. This principle is not a slogan, it is a quantitative statement. This is not a philosophical claim, it is a measurable one, and it can be tested in multiple ways. Pions decay mostly to muons rather than electrons, not because the weak force prefers muons, but because helicity and mass factors reshape the probability. The weak interaction has a chiral structure, and the pion spin constraints suppress the electron channel more strongly. When calculations include those factors, the standard model predicts the ratio precisely. If you could freeze the decay in a slow-motion visualization, you would see the pion vanish and two nearly invisible lines of momentum emerge. One line corresponds to a neutrino, which slips away without a trace, and the other corresponds to a charged lepton that leaves a track. The muon track is longer and more common, while the electron track appears less often, not due to favoritism but due to the geometry of spin and motion. The ledger's prediction is subtle, yet it lands on a sharp number. Kaon decays offer similar tests, with different energies and different hadronic uncertainties, so they provide an independent audit. W bosons decay to each charged lepton and its neutrino, and the branching fractions can be compared across families. Z bosons decay to lepton pairs, and the widths can be measured with extreme precision, especially in clean electron, positron collider environments. Each channel is a different window onto the same principle. At facilities like CERN's LEP in the late 20th century, Z bosons were produced in enormous numbers, and their decays were catalogued with meticulous care. The Z's total width encodes how many decay modes are available, and its partial widths reveal how strongly it couples to each species. Those measurements helped confirm that there are 3 light neutrino types, because additional light neutrinos would have increased the invisible width. Even here, the family pattern appears as a measurable count. Each comparison becomes an audit, and the audit is unforgiving because the standard model's predictions are crisp. If the muon couples slightly differently than the electron, the ratios drift in ways that statistics cannot easily hide. If the tau hides a new interaction, its decays would carry a fingerprint that cannot be blamed on mass alone. The detective work is not about finding a dramatic failure, but about finding a tiny mismatch that refuses to average away. This is why universality tests feel like detective work, with each decay channel acting as a separate witness. The standard model gives a sharp prediction, and experiments look for a deviation that persists across detectors and methods. A tiny mismatch can imply a new force, a new particle, or a new symmetry-breaking pattern. The smallest anomaly can be the loudest clue. So far, universality mostly survives, and that survival is part of the suspense rather than an ending. The success makes the repetition look even more exact, because the copies behave like copies under the forces. The more perfectly the interactions align, the more the mass differences stand out as the lone exception. The ledger looks consistent, but it also looks unfinished. The standard model also tracks lepton number, a bookkeeping rule that labels which reactions are allowed and which are forbidden. In its original form, it effectively conserves 3 separate family numbers, at least in the simplest version of the theory. Electron flavor, muon flavor, and tau flavor act like separate accounts, and the rules keep each account balanced. This bookkeeping is not arbitrary. because it matches the decay patterns that were observed for decades. This explains familiar decay patterns in a way that feels almost mechanical. A muon decays into an electron plus a muon neutrino and an electron antineutrino, keeping the flavor books balanced. A tau can decay into a muon or an electron, again with neutrinos carrying away the missing flavor. The neutrinos are not decorative because without them the accounting would fail. For decades these rules looked exact, and their apparent exactness shaped how physicists thought about generations. They made the generations feel like separate lanes, connected only by the weak interaction's ability to create neutrinos. They also made neutrinos seem like passive partners rather than active players, because they were assumed to be massless and almost invisible. The ledger's neatness encouraged the belief that the bookkeeping was fundamental. Neutrino oscillation changes the meaning of those lanes, and it does so with a simple but profound observation. A neutrino produced as one flavor can later be detected as another, which means flavor is not a fixed identity during propagation. The separate family numbers are not fundamental conservation laws in nature, at least not in the neutrino sector. The ledger's columns blur while the neutrino travels. Oscillation implies mixing between neutrino states, and mixing implies mass differences, because identical masses would not produce the observed interference pattern. In quantum terms, the flavor states are superpositions of mass states, and the phases evolve differently as the neutrino moves. That evolving phase difference produces oscillation, like two slightly different musical notes creating a beat pattern. It forces an extension of the standard model because massless neutrinos cannot oscillate. The evidence for oscillation did not arrive as a single dramatic event, but as a convergence of puzzles. Solar neutrino experiments saw fewer electron neutrinos than expected, and atmospheric neutrino measurements found a flavor-dependent deficit. Over time, the simplest explanation became the most compelling. Neutrinos were changing identity. What looked like missing particles was instead a transformation in flight. The conservation story becomes layered once oscillation is accepted as real. Total lepton number might still be conserved, or it might not, depending on what neutrinos really are. Individual family numbers are definitely violated in the neutrino sector, and that fact will echo later in questions about matter and antimatter. The ledger still works, but it now has erasures and annotations. The standard model's elegance is that it predicts what it is built to predict, and it does so with astonishing accuracy. Given the field content and the couplings, it computes cross-sections, lifetimes, and radiative corrections that match experiments across many orders of magnitude. It explains why the electron's magnetic moment matches theory to many decimal places, after accounting for quantum fluctuations. That agreement is one of the most stringent tests in all of physics. Those quantum fluctuations are not abstract, because they are the constant jitter of fields interacting with one another. In the equations, particles emit and reabsorb virtual quanta, and those loops shift measurable quantities. In the lab, those shifts appear as tiny deviations from simple classical expectations. The fact that the standard model tracks them so well is why its ledger is trusted. Yet it cannot answer the question that the ledger itself raises, and the question is as simple as it is deep. Why are there 3 generations rather than 1 or 5 when the forces would still work with a different count? Why do the Yukawa couplings span orders of magnitude with no apparent pattern, as if nature chose them from a wide menu? The standard model accepts these as inputs, but it does not justify them. The model also cannot tell us why the neutrino masses are so small, especially compared to the charged leptons. It can accommodate them only by adding new terms or new particles, like right-handed neutrinos or higher dimensional operators. Those additions can be written consistently, but they are not demanded by the minimal ledger. The need for them suggests that the lepton sector is where the standard model's boundaries are most visible. This is where the documentary's central question tightens, because the repetition is too clean to ignore. If the forces treat the generations the same, then the differences must come from mass and mixing. If mass and mixing are set by parameters the model cannot compute, then the generations are clues to missing principles. The copies are not redundant once you treat them as evidence. The mystery is not only laboratory-sized, and that is part of what makes it compelling. In the early universe, the temperature was high enough that muons and taus were common, not exotic, because energy routinely became mass. When the cosmic soup was dense and hot, every available field could be populated, and the heavy copies were simply part of the thermal inventory. The ledger was not a table on paper, it was a living census of what could exist. As the universe expanded and cooled, heavy leptons disappeared through decay and annihilation, leaving behind lighter survivors. But their presence mattered while they lasted, because they shared energy with other species and influenced reaction rates. Even brief populations can leave lasting imprints through what they heat and what they dilute. In cosmology, timing is everything, and leptons help set the clock. You can visualize this era as a bright, opaque fog of particles, where collisions happen faster than any human intuition can track. In that fog, muons and taus flicker into existence, scatter and decay, their energy redistributed into lighter particles. The universe is not quiet. It is a furnace with expanding walls. The heavy copies are not curiosities there. They are part of the thermal equilibrium. Neutrinos connect lepton physics to cosmic history more directly, because they decoupled early and then streamed almost freely. They stopped interacting efficiently when the universe was only seconds old, and after that they carried information forward with minimal disturbance. A relic neutrino background should still fill space today, carrying a fossil record of early conditions. It is like a cosmic afterglow, but far harder to detect than light. Neutrinos also affect expansion and structure formation in ways that can be measured indirectly. Their number and energy density influence how fast the universe cooled during nucleosynthesis, when light elements were forged. Their tiny masses, though small, suppress the growth of small-scale structure, because fast-moving neutrinos smooth out density fluctuations. Cosmology becomes a neutrino experiment by other means, using galaxies and the cosmic microwave background as detectors. So the lepton ledger is written in two places at once, and the two copies must agree. It is written in collider data and decay tables, where universality is tested line by line with controlled beams and calibrated detectors. It is also written in the sky, where relic neutrinos and early thermal histories constrain what particles could exist. The same fields that govern AP and decay also shape the universe's first minutes. The standard model passes many of these tests, which is part of its power and part of the frustration. It gives us a near-perfect description of how lepton families behave, both in the lab and in cosmic history. It does not give us the reason the families exist, or why their masses are spaced the way they are. The ledger is accurate, but it is not explanatory in the way a deeper theory might be. That gap is not a minor missing detail, because it touches the origin of mass and the origin of a symmetry. If neutrinos carry new phases that violate CP symmetry, they could help explain why matter survived over antimatter. If lepton number is not absolute, then the early universe could have converted lepton asymmetry into baryon asymmetry through known electroweak processes. These are not detached speculations, because they are tied to measurable properties like mixing angles and phases. Those possibilities are not yet answers, but they are directions, and directions matter when the map ends. They tell us why physicists treat lepton families as more than redundancy, even when the forces treat them as copies. The copies might be the entry point to physics that the standard model cannot see. The ledger's repetition could be the outline of a missing chapter. For now, we hold on to the clearest statement the model makes, because clarity is rare in a mystery. The electron, muon, and tau are distinct fields with identical gauge charges, and the forces interact with them in the same way. Their masses come from different Yukawa couplings to the same Higgs background, and those couplings are measured, not derived. The ledger is consistent, but it is silent on motivation. We also hold on to the clearest statement the universe makes, and it is written in neutrino data. Neutrinos oscillate, so flavor is not fixed, and the generation labels are not perfectly conserved. The template repeats, but the boundaries between templates blur as neutrinos propagate. The ledger's neat columns are real, yet nature writes between them. This is the chapter's tension, and it is the tension that keeps the story moving. The standard model is an elegant ledger that predicts almost everything we ask of it, from scattering rates to subtle quantum corrections. The ledger cannot explain why its most obvious pattern is repeated 3 times. It can describe the copies, but it cannot justify them. To understand why the copies exist, we have to follow the first copy ever found, because history often reveals what equations conceal. We have to follow the muon, from its shock discovery to its role as a precision probe, and then watch how it became a tool for exposing tiny cracks. The next chapter begins where the ledger meets the anomaly, and where a duplicate becomes a clue. The standard model's ledger looks tidy on paper, but history found the copies first, etched into photographs of vapor and light. The muon enters as an intruder from the sky, carrying the electron's charge and spin, yet refusing the electron's role in ordinary matter. It arrives not as a prediction fulfilled, but as a track that should not exist. Too clean, too penetrating, and too heavy to ignore. In the 1930s, cosmic rays became a natural particle beam, striking the upper atmosphere and triggering cascading showers of secondaries. Above the clouds, unseen primaries, mostly high-energy protons and nuclei, slam into nitrogen and oxygen, producing pions and kaons that quickly decay. Those mesons are short-lived intermediates, and their decays seed the shower with muons and neutrinos that inherit much of the original momentum. What reaches the ground is not the original projectile, but a rain of byproducts, each one a clue to the collision that happened kilometers overhead. On screen, the era looks almost quiet. A dark lab, a glass chamber, a sudden flash, and then a delicate thread of droplets. Cloud chambers, nuclear emulsions, and early Geiger counters recorded curved tracks in magnetic fields, and some tracks looked electron-like but too straight. A particle with the same negative charge was bending less, which implied far greater momentum or far greater mass. In the grain of old film, you can almost feel the tension between what the eye sees and what the equations demand. Curvature in a magnetic field is not a stylistic flourish, it is a measurement. Radius tells you momentum per unit charge. For a given magnetic field, a light particle curves tightly, while a heavy one, moving comparably fast, draws a broader arc. The photographic plates did not merely show a line, they showed a quantitative mismatch, as if nature had changed the scale without changing the sign. Even the thickness of the track mattered, because ionization density and range were early proxies for speed and mass. Physicists tested the obvious explanation that it was a proton, because protons are heavy and penetrate. Protons also leave a characteristic trail of ionization, because they move more slowly at the same momentum and deposit energy differently. The ionization did not match a proton, and the curvature did not match an electron, so the track sat between categories. It behaved as if it were light enough to be minimally ionizing, yet heavy enough to resist bending, an uncomfortable combination for the taxonomy of the time. That between was the unsettling part, an object that refused the neat bins of the era. It behaved like a lepton in charge and in its clean single track, yet it carried itself like something heavier. The result was a new charged particle, about 207 times the electron mass, and apparently fundamental. In today's units, that is about 5.7 MeV of rest energy, a number that later becomes a constant in countless calculations. The discovery felt like redundancy, not completion, because it solved no immediate puzzle in matter as people then understood it. It did not bind atoms into chemistry, and it did not stabilize nuclei the way the neutron had. It was simply there, a second electron that nature did not seem to need. When a new particle fails to explain an existing mystery, the mind turns to a sharper question. What hidden rule produced it anyway? That mood is captured in the famous line often attributed to I. Rabbi, who ordered that? A sentence that lands like a dropped instrument in a quiet room. The question was not about measurement error, but about meaning, because the ledger had gained an unexplained duplicate. If the electron already did its job perfectly, why would the universe mint a heavier version and then hide it in cosmic rain? The remark also reflects a cultural moment, when particle physics still hoped for a small cast of characters, rather than a growing ensemble. The muon's basic identity is simple to state and hard to justify in any narrative of necessity. It is a lepton with electric charge -1 and spin 1/2, like the electron, and it obeys the same quantum statistics. It couples to photons and to the weak bosons with the same electroweak charges, so forces treat it as a copy. In a detector, it is not exotic in behaviour, which makes its existence feel even more arbitrary. In modern language, it sits in the same pattern of gauge interactions, sharing the same electric charge and the same weak isospin assignments. That means it radiates photons, it responds to magnetic fields, and it participates in weak processes that change one lepton into another. If you only watched how it interacts, you could mistake it for an electron wearing heavier boots. Yet mass is not a cosmetic detail, because in quantum field theory, mass sets the scale of what distances a particle can probe. Its differences are mass and instability, and those differences make it useful in ways the electron cannot match. The muon is heavy enough to punch through material with less deflection and less radiative loss than electrons, because Bremsstrahlung is suppressed by mass. It also lives long enough to be timed, tracked, and used as a probe. In practical terms, a muon behaves like a near-ideal minimum ionizing particle across a wide energy range, leaving a steady, interpretable signal. The muon's mean lifetime at rest is about 2.2 microseconds, a number that sounds brief until you translate it into distance. Even at ordinary relativistic speeds, that is long enough for a muon to cross hundreds of meters before it decays. In detectors, that lifetime becomes a clean exponential clock and a clean test of relativity. The decay is random for any single muon, yet statistically precise across millions of events. A microsecond is also an engineer's unit, which matters for the story that follows. It is long enough to build electronics around, long enough to trigger on, and long enough to correlate with other signals in a multilayer detector. The muon is ephemeral, but it is not uncatchable. That balance, short-lived but measurable, turns a cosmic curiosity into a laboratory workhorse. Cosmic ray muons create an early paradox that becomes a teaching moment, because the sky seems too far away. They are produced high in the atmosphere, yet they are detected at sea level in large numbers, even inside buildings and underground stations. If you compute their travel time using classical intuition, most should decay before reaching the ground. The paradox is not subtle, because the flux is large enough to measure with simple counters and patient counting. The geometry is simple, and that simplicity makes the contradiction sharp. Production happens at altitudes of several kilometers, and the muons move near the speed of light, but not infinitely fast. Without relativity, a 2.2 microsecond lifetime would allow only a few hundred meters of travel, and the ground should be quiet. Instead, the ground is noisy with muons, as if the atmosphere were transparent to a particle that ought to vanish midair. Special relativity resolves the paradox through time dilation, and it does so with numbers you can put on a chart. In the muon's frame, the atmosphere is length contracted, and the ground arrives sooner than you would expect. In our frame, the muon's internal clock runs slow, so its 2.2 microseconds stretches into tens of microseconds at high speed. The key is that both descriptions preserve the same space-time interval, even though they distribute time and distance differently. The two descriptions are not competing stories. They are the same physics seen from different vantage points. Lorentz factors of 10 or more are common for cosmic muons, and that factor multiplies the lifetime you observe. The result is a particle that should have died in the sky, yet arrives at your detector, alive because time itself is frame-dependent. When you watch the counts rise on a meter, you're watching a relativistic correction made tangible. This is not a philosophical point, because the numbers match across altitudes and energies. The measured flux of muons at different elevations agrees with relativistic predictions, and the angular distribution agrees with the geometry of their creation. A stray particle from cosmic rays becomes a practical confirmation that time depends on motion. Even the dependence on zenith angle, longer paths for slanted muons, matches the expected survival probabilities. Visually, the demonstration is almost cinematic. A mountain station, a sea-level lab, and a graph where the counts fall exactly as relativity says they must. The muon becomes a messenger that carries Einstein's equations into the realm of counting clicks. It is a reminder that spacetime is not an abstract stage, but a measurable component of the experiment. The atmosphere becomes a natural baseline, and the muon becomes a stopwatch that refuses to tick at one universal rate. Muon decay reveals the weak interaction in action, and it reveals why neutrinos had to be real rather than convenient. The dominant decay is muon to electron plus 2 neutrinos, a three-body final state that spreads energy continuously. More precisely, a negative muon decays into an electron, a muon neutrino, and an electron anti-neutrino. The positive muon mirrors this with antiparticles, an early hint that the weak interaction cares about handedness, but respects charge bookkeeping. That bookkeeping, 2 different neutrino flavors, matters, because it encodes the idea of lepton family number. The muon does not simply disappear into an electron and something, it leaves behind a muon-flavored neutrino as a kind of signature. Even in decay, the muon insists on being a distinct species. Later experiments would confirm this distinction directly, showing that neutrinos produced with muons behave differently from those produced with electrons. The decay is mediated by the W boson in the standard model picture, although the W is far too heavy to appear as a real particle here. The muon emits a virtual W and turns into its neutrino partner. Then the W becomes an electron and an electron anti-neutrino. The process links lepton families through a shared weak structure, even when masses differ. In plain terms, the weak force is the only interaction that can rewrite the particle's identity while conserving the deeper charges. In older language, before the W was directly observed, this was described by Fermi's theory as a contact interaction. That historical step matters because it shows how the muon helped shape the weak force into a coherent framework. The muon's decay rate, and the way it scales, became a calibration point for weak coupling strength. The lifetime is not just a number, it is a measurement of how strongly the muon couples to the weak interaction at low energies. The neutrinos matter because the decay kinematics demand missing energy and momentum, and the demand is strict. If the muon decayed into only an electron and a photon, the electron energy would be fixed by two-body kinematics. Experiments saw a broad spectrum of electron energies, which implied invisible particles carrying variable shares. That continuous spectrum is the kind of clue that survives changes in apparatus, because it is dictated by conservation laws. That spectrum is not a subtle feature, it is a fingerprint, smooth, continuous, and impossible to fake with a single unseen photon. It also carries angular information, because the muon spin biases the directions of the decay products. In precision studies, the electron energy and angle become a map of the underlying weak interaction. When muons are polarized, the asymmetry in electron emission becomes a direct readout of the weak force's chiral structure. This was one of the strongest arguments that neutrinos were not bookkeeping fiction, because conservation laws had to hold event by event. They were required to conserve energy, momentum, and angular momentum in a consistent way, not merely on average. The muon therefore helped turn the neutrino from a hypothesis into an experimental necessity. In retrospect, it is striking that an unseen particle became unavoidable because a seen particle refused to produce a sharp line in an energy plot. There is a deeper conceptual point hiding in that necessity. The weak interaction violates parity, meaning it distinguishes left from right, and the muon's polarized decays display that asymmetry. When you watch decay electrons prefer certain directions relative to spin, you are watching a fundamental preference built into the laws. The universe, at the level of elementary processes, does not treat mirror images as equivalent, and the muon makes that bias measurable. The muon also helped clarify what the weak force is not, by showing what it can do that other forces cannot. It is not electromagnetism, because it changes particle identity rather than only momentum and phase. It is not the strong force, because leptons do not feel colour and do not bind into hadrons. It is a separate interaction with its own heavy mediators and its own selection rules. That separation becomes clearer when you compare event topologies, not just equations. On camera, this separation can be made visual with a simple contrast. Strong interactions leave jets, sprays, and bound states, while muons often leave a single clean track that keeps going. Electromagnetism bends the track, but it does not transmute the particle into another lepton. The weak force is the one that changes names. In the layered architecture of a modern detector, the muon's persistence becomes a signature. Inner tracker, calorimeters, then the outer muon chambers lighting up in sequence. As the muon story matured, it shifted from mystery to tool. Because muons penetrate, they became natural probes of material thickness and density, and their abundance made them practical. Cosmic muons can be counted after passing through rock, concrete, or metal, and the deficit maps hidden structure. What began as an atmospheric byproduct becomes, with enough statistics, a kind of passive imaging technology. This technique is sometimes called muon radiography, and it works like X-rays with a different source and different constraints. The source is the sky, and the detector is placed below or beside the target, often for weeks or months. The muon's high energy and weak scattering let it traverse volumes that stop ordinary radiation. Multiple scattering still occurs, but the angular deviations can be modelled, and the surviving flux still encodes density along each path. The physics is straightforward, but the imagery is striking. A detector array in a tunnel, a pyramid silhouette, a volcano flank. Each muon that arrives is a line of evidence, and many lines become a density image. Where the rock is thicker, fewer muons survive, and the map darkens. The method is slow, but its slowness is part of the aesthetic. Nature provides the beam, and humans provide the patience. Unlike X-rays, muons arrive from many angles, so the reconstruction is a kind of natural tomography. multiple detector planes measure direction, and the atmosphere provides the beam without a machine. It is a quiet partnership between cosmic violence and human patience. High energy impacts in the stratosphere, counted one by one in a darkened room. When the image finally resolves, it feels less like a snapshot and more like a long exposure photograph of invisible traffic. The muon's mass also makes it a microscopic probe in a different way, inside atoms where quantum mechanics sets the scale. A slowed muon can be captured by a nucleus and replace an electron, forming a muonic atom. Because the muon is heavier, its Bohr radius is smaller, and it orbits much closer to the nucleus. The capture process often produces a cascade of X-rays as the muon drops through energy levels, and those photons carry precise information. The scaling is dramatic and easy to state. For hydrogen-like systems, orbital size shrinks roughly in proportion to the lepton mass. Replace an electron with a muon, and the orbit contracts by about a factor of 200. What was a diffuse electron cloud becomes a tight, fast orbit deep inside the atom's usual boundary. In heavy nuclei, the muon can orbit so close that relativistic and finite-size effects become dominant rather than minor corrections. That closeness amplifies sensitivity to nuclear size and charge distribution, because the muon's wave function overlaps the nucleus. Energy levels shift because the nucleus is not a point, and because vacuum polarization modifies the effective potential. Spectroscopy of muonic atoms becomes a ruler for the proton radius and for nuclear structure. When those measurements disagree with expectations, the disagreement is not a philosophical debate, it is a numeric tension in a spectrum line. Visually, the comparison is almost like changing lenses. The ordinary atom is a wide, soft blur, while the monic atom is a sharp close-up where the nucleus is no longer a distant center. In that close-up, small corrections matter, and the vacuum itself becomes part of what you measure. The narrator can linger on the idea that empty space is not empty, because the muon's orbit turns emptiness into a measurable influence. This is where the muon begins to act like a detector for quantum fluctuations, not merely a particle to be catalogued. In quantum field theory, the vacuum is filled with virtual particles that appear in loops, affecting forces at short distances. Those loops shift energy levels and magnetic properties by small, calculable amounts. The muon, because it is heavier, samples shorter distances in the same electromagnetic field, and short distances are where new physics likes to hide. Vacuum polarization, for example, can be pictured as the photon briefly splitting into a virtual electron-positron pair that screens charge. That screening changes the effective Coulomb potential at small radii, and a muon orbiting close to the nucleus feels it strongly. The vacuum is not empty space, it is an active medium with measurable consequences. Even if the picture is simplified, the outcome is concrete. Spectral lines move, and the shifts can be predicted and tested. The heavier the lepton, the more strongly it feels short-distance physics in these loop effects, because it samples smaller distances. The muon is about 200 times heavier than the electron, so its sensitivity to heavy virtual particles is enhanced. A small new interaction that barely nudges the electron can leave a larger imprint on the muon. This is a recurring theme in precision physics. Heavier probes often amplify subtle corrections without requiring higher collision energy. This logic sets up the modern tension around the muon's magnetic moment, where tiny becomes important. A charged spinning particle behaves like a tiny magnet, and the strength is tied to a factor called G. In the simplest Dirac theory for a point like fermion, G equals 2. That statement sounds like a detail, yet it is one of the cleanest bridges between abstract theory and measurable numbers. That Dirac result is not a guess. It is a consequence of combining quantum mechanics with special relativity for a spin-1-2 particle. It is also a baseline that makes deviations meaningful, because any shift must come from interactions beyond the simplest picture. In that sense, G is a ledger entry for how the particle talks to the quantum vacuum. The muon's G becomes especially interesting because it is both measurable in the lab and sensitive to many kinds of virtual contributions. Quantum mechanics and relativity do not stop at the Dirac result, because fields interact with themselves and with other fields. The muon can emit and reabsorb photons, and it can fluctuate through virtual particle loops involving known fields. These radiative corrections shift G slightly above 2, and the difference is called the anomalous magnetic moment. The anomaly is not a sign of failure, it is a sign that quantum fields are alive with self-interaction. Physicists write it as A just mu equals G minus 2 over 2. a compact symbol for a long calculation. The standard model predicts AEGS and mu by adding contributions from quantum electrodynamics, the weak interaction, and hadronic effects from quark and gluon dynamics. Each contribution is small, yet the sum can be predicted with impressive precision. The extraordinary part is not that the number is close to 2, but that theory and experiment can argue about parts per billion. The QED part is the showcase, because it can be computed to extraordinarily high order in perturbation theory. Diagrams with multiple photon loops contribute, each one smaller than the last, and together they form a numerical triumph. The weak contribution is smaller, but it is conceptually important because it brings in W and Z loops. Those loops remind you that even at low energies, heavy particles leave faint fingerprints through virtual effects. The hadronic part is the difficult one, because quarks and gluons do not behave perturbatively at the relevant energies. Hadronic vacuum polarization and hadronic light-by-light scattering enter as subtle corrections, and they must be inferred from data or from lattice simulations. The muon, ironically, is sensitive to the messiest part of the standard model. In this sense, the muon anomaly is also a stress test of our ability to translate strong interaction complexity into precision predictions. The experimental measurement is conceptually clean but technically demanding, and it looks like precision choreography. You store polarized muons in a magnetic ring, and you watch their spin precess relative to their momentum as they circulate. The precession frequency depends on AILMU, and the decay electrons carry information about the spin direction. The apparatus turns an abstract quantum property into a rhythm, an oscillation in time that can be counted and fit. In the ring, the muon is both the subject and the clock, because its spin is a built-in pointer. As the spin turns, the probability of emitting a high-energy decay electron in a given direction oscillates. Detectors around the ring record those electrons, and the oscillation frequency becomes the quantity you fit. The visual can linger on the ring's symmetry, muons circling, detectors flashing, and a sinusoidal curve emerging from what looks like random decay. This is where the muon's 2.2 microseconds becomes a feature, not a limitation, because you can stretch it with speed. Time dilation in the ring extends the observed lifetime, giving many turns to measure precession before the muons decay away. The same relativistic effect that brings cosmic muons to sea level also enables precision in the lab. Relativity is no longer a mountain versus sea level demonstration, it is an engineered design parameter. The ring itself becomes a character in the narrative, because it must be controlled at the level of parts per billion. Magnetic fields are mapped and monitored, electric fields are tuned, and systematic errors are hunted like faint echoes. Every correction is a promise that the remaining discrepancy, if any, is real. Even temperature drifts, mechanical vibrations, and tiny field inhomogeneities become suspects, because the measurement is only as trustworthy as its least glamorous detail. The suspense comes from a persistent mismatch between prediction and measurement, a mismatch that refuses to vanish with improved apparatus. Experiments at Brookhaven and later at Fermilab reported values that sit above a widely used standard model expectation. The discrepancy is small in absolute size, yet large enough to tempt the phrase new physics. In Narration, the tension is best framed as restraint. Physicists do not want a miracle, they want a robust inconsistency. Small here means a change in the 6th or 7th decimal place, which sounds like nothing until you realize what it represents. It represents the net influence of all virtual particles the muon can briefly become, including ones we have never seen directly. A tiny shift is a census of the invisible. The question is whether the census is incomplete because the standard model is missing residents, or because our accounting of hadronic effects still has uncertainty. The careful version of the claim is narrower and more interesting, because it separates measurement precision from theoretical uncertainty. The measurement is precise, and the theory is precise, but the theory depends on difficult hadronic contributions. Those hadronic terms can be estimated using data-driven methods or lattice calculations, and different approaches shift the predicted value. The story becomes less like a single number and more like a dialogue between methods, each with its own assumptions and error budgets. Data-driven methods connect hadronic vacuum polarization to electron, positron annihilation into hadrons, using dispersion relations that translate one measurement into another. Lattice QCD, by contrast, simulates quarks and gluons on a spacetime grid, extracting the same contribution from first principles. The two approaches are converging, yet they still leave room for tension. When they disagree, the disagreement is not merely academic, it changes whether the anomaly looks like a crack in the model or a crack in our calculation. So the anomaly is both a crack and a test of our tools, and that dual meaning is why it matters. If the discrepancy survives improved theory and improved measurement, it points to additional loop contributions from unknown particles or forces. If it fades, it still teaches us how quantum chromodynamics leaks into precision observables. Either way, the muon forces a confrontation between what we can measure cleanly and what we can compute reliably. Either outcome keeps the muon central, because the question is now structural rather than merely historical. Why does nature provide a heavier lepton that amplifies quantum loops, if not to reveal something hidden? The muon looks like a copy, yet it behaves like an instrument, and instruments in science are not judged by how pretty they are, but by what they can detect when everything else looks quiet. That instrument-like role raises a quiet, unsettling observation. The standard model contains patterns that look designed for cancellation and consistency, yet it also contains repetitions that look gratuitous. Are generations a clue to deeper symmetry, or are they a record of accidents frozen into the laws? If the pattern is meaningful, then the muon is not a spare part, it is a signpost. The culture of modern particle physics is built around that duality between discovery and audit, between building and checking. CERN and other accelerator centers search directly for new particles at high energy, smashing beams together to create heavy states. Precision experiments, often elsewhere, search indirectly by measuring tiny deviations that virtual particles can cause. Both strategies depend on the same quantum field theory language, yet they interrogate it from opposite directions. These two approaches constrain the same underlying quantum field theory, even when they feel like different disciplines. A new particle that shifts muon G-2 should also affect collider events, rare decays, or electro-weak precision fits. If colliders see nothing, the allowed explanations for G-2 become narrower and more specific. The absence of fireworks at high energy does not end the story, it sharpens the list of plausible whispers. This interplay is not a footnote, because it shapes what physicists believe and what they build next. High-energy null results can rule out simple new force models, even if they would explain the anomaly. Precision results can motivate targeted searches, even when the new particle is too heavy or too weakly coupled to appear directly. The field advances by this push and pull, where one experiment's silence becomes another experiment's guidance. On screen, the contrast is vivid. A vast collider tunnel with thousands of magnets, then a smaller ring experiment obsessing over field uniformity. One chases fireworks, the other chases whispers, yet both interrogate the same vacuum. The muon sits between them, a particle that can be produced in bulk and measured with delicacy. In montage, you can cut from roaring accelerator infrastructure to the quiet patience of calibration, and the muon belongs to both worlds. The muon therefore sits at a crossroads between scales, and that position is part of its narrative power. It is produced in messy hadron collisions and in clean electroweak processes, and it is also produced by cosmic rays for free. It can be studied as an isolated lepton, and it can be used as a handle inside complex events. That versatility is why muons are so often the tag that tells physicists where to look in a sea of particles. In collider detectors, muons are prized because they often escape the dense calorimeters, leaving long tracks in outer chambers. That makes them clean signatures in a chaotic environment, like a straight voice cutting through a crowd. When an event contains muons, it often contains a story worth reading. The visual language is almost universal. In a detector hits, then nothing, then a final set of aligned signals far outside, announcing that a muon passed through. The cosmological connection follows naturally once you accept the loop logic, because the vacuum is the same everywhere. If a new particle contributes to muon G-2 today, it could have been present in the early universe when temperatures were high. It could have changed the energy density, altered freeze-out histories, or opened new annihilation channels. A discrepancy in a laboratory ring can therefore echo into the inventory of the early cosmos, where particle species determine how the universe cools and evolves. Some candidate explanations live in a dark sector, with weak couplings to ordinary matter that make them hard to see directly. Such particles could also be related to dark matter production, or to hidden forces that shape cosmic structure over billions of years. Others could introduce new sources of CP violation that matter for the matter, antimatter asymmetry. The point is not that one measurement solves cosmology, but that it can constrain what kinds of hidden ingredients are even allowed. The point is not that G-2 automatically explains cosmology, because the universe is not solved by one number. The point is that a lab-scale discrepancy can imply new fields, and new fields rewrite the early universe inventory. The Muon anomaly, if real, would be a message from the vacuum about what else exists. It would also be a reminder that virtual particles, though fleeting, can still shape the evolution of everything when the universe was young and dense. It also invites a more reflective question, one that fits the Muon's role as an intruder. How many clues have we already recorded filed away as anomalies because they did not fit the dominant narrative of the time? The Muon itself was once such a clue, obvious in hindsight, baffling in the moment. In science, the hardest step is often not measuring the unexpected, but deciding that the unexpected deserves a new category. This returns us to the documentary's central question about generations, because the Muon is the first clear sign that the electron is not alone in its template. It is a second-charged lepton with the same interactions, and its existence forces the idea of families. Once you accept one copy, you must ask whether the copying stops, and if it does not stop, you must ask what principle is doing the copying and what it is trying to preserve. Yet the Muon also refuses to be merely redundant, because it is uniquely positioned in mass and accessibility. It is heavy enough to magnify short-distance physics, and light enough to be produced and controlled in huge numbers. It is unstable, yet stable enough to measure with exquisite precision. That combination is rare in particle physics, where the most interesting particles are often too short-lived or too difficult to isolate. In that sense, the Muon is a bridge between the everyday and the fundamental. It falls through your body by the thousands each minute, yet it also encodes the subtlest quantum corrections we can calculate. It is both common and profound, an ordinary visitor carrying extraordinary information. If you pause on that fact, it becomes almost unsettling. The universe rains precision probes onto the Earth continuously, whether we build detectors or not. So Chapter 3 ends with a tension rather than a resolution, because the ledger still does not explain itself. The Muon began as a cosmic intruder that did not fit the pattern, and it became a precision probe that tests the pattern's limits. If the anomaly holds, the first copy may be pointing beyond the ledger. If it fades, the Muon still stands as the particle that taught us how to interrogate the vacuum with numbers. Now the story escalates, because nature did not stop at one extra copy. Redundancy becomes a rule. A third charged lepton exists, far heavier and far shorter lived, and it deepens the redundancy into a structure that demands explanation. The next chapter follows that heavier shadow, the tau, and asks what 3 generations are trying to tell us. The Muon already felt like an unnecessary echo of the electron's field. The tau makes that echo a pattern. 3 charged leptons, same charges, wildly different masses. In the standard model ledger, they look like copies with different weights, and that resemblance is exactly what makes them unsettling. On paper, the charged leptons are almost too simple, and that simplicity is part of the provocation. Each one carries electric charge. Each one has spin 1/2, and each one couples to the photon with identical strength. Their magnetic moments follow the same basic quantum rule, even though tiny loop corrections differ. Yet the masses climb by orders of magnitude, as if nature kept the same blueprint but changed the scale. That scaling is not cosmetic, because mass in quantum field theory is not just heaviness. Mass sets how strongly the Higgs field must couple to a particle to give it inertia, and it sets which decays are kinematically allowed. It also controls how quickly a particle can shed energy through radiation, and how sharply it curves in a magnetic field. The tau therefore inherits the electron's identity, but it lives in a very different experimental regime. The tau is the heaviest charged lepton, about 1.777 GeV, and it decays almost immediately. That mass is roughly 3,500 times the electrons and about 17 times the muons, which is why its decay options explode. It can fall apart into lighter leptons or into hadrons because it sits above the threshold for many mesons. In practice, that means the tau can create pions, kaons, and resonant combinations that the muons simply cannot afford. Its lifetime is roughly 10-13 seconds, so it travels fractions of a millimeter even when boosted. In its own rest frame, the mean decay length is only about 87 micrometers, thinner than a human hair, so even a fast star leaves no long leisurely track. When it is produced at high energy, relativity stretches the flight distance, but the scale remains stubbornly small. A detector must therefore treat the tau as a vertex problem, not a track problem. That short lifetime changes the meaning of discovery, because you do not catch a tau as a long track. You infer it from a displaced decay point, missing momentum, and a distinctive mix of debris. The tau is not a particle you see in the ordinary detector sense. It is a hypothesis that keeps winning against alternatives. In the language of analysis, it is a reconstructed object whose credibility comes from consistency across many variables. Visually, that inference begins as a sparse, almost minimalist event display, and then becomes a bookkeeping drama. A few curved tracks arc outward in the magnetic field, calorimeter cells light up in compact islands, and then the accounting fails. Energy seems to vanish. The tau enters the story as a missing piece, not as a bright line. You feel it as an imbalance, like a sentence with a word removed, where the grammar still points to what must be there. In the mid-1970s, electron-positron colliders became the cleanest stage for new leptons, and that cleanliness mattered more than raw energy. The reason is almost philosophical. When you know the initial state precisely, conservation laws become sharp tools rather than vague guidelines. In Ipsius collisions, the beams carry well-defined energy, and the collision has no messy remnants of protons. The detector's job becomes closer to accounting than archaeology. At these machines, the initial state is known, and energy accounting becomes a weapon. Momentum in the plane transverse to the beam should sum to nearly zero, and the total visible energy should match the center of mass energy, unless something invisible escapes. That unless is where neutrinos, and therefore taus, hide. It is also where careful calibrations become part of the physics, because an apparent deficit must be separated from instrumental loss. The tau first appeared as events with an electron or muon on one side, and hadrons on the other. In the detector, it looked like a two-hemisphere world. One hemisphere clean and leptonic, the other clustered and jet-like, with both sides oddly under-energized. The totals did not balance unless invisible particles carried energy away. Even the angles felt suggestive, because the two hemispheres tended to recoil against each other, as if born from a pair. Missing energy was not a detector glitch, because it repeated with consistent kinematics and with stable detector conditions. The distributions lined up across many events, and the imbalance pointed in directions that made physical sense. If it had been a calibration error, it would have smeared broadly. Instead, it formed a recognizable pattern. The missing momentum also correlated with the visible objects in ways that matched three-body decays, rather than random noise. The simplest explanation was a new lepton pair produced, each decaying with neutrinos. In modern language, E plus is test, followed by T decays that always include at least one neutrino. That hypothesis did not merely fit one event display, it fit an entire population. It predicted rates, angular distributions, and energy spectra that could be checked as the data sample grew. The signature was asymmetric because tau decays are varied, and often one-prong or three-prong. A narrow jet with low track multiplicity became a recurring clue. It was not the wide, busy spray of a typical quark jet, but something tighter, more disciplined, as if the decay were constrained by a single parent. That collimation is partly geometric, because a boosted tau squeezes its decay products into a small cone. A tau decay always includes at least one tau neutrino, and often two neutrinos in leptonic modes. Those neutrinos escape, so the visible energy is systematically reduced. The detector sees what is charged and what showers electromagnetically or hadronically, but neutrinos pass through as if the apparatus were not there. They leave no hits, no clusters, and no tracks, only a deficit that must be inferred from everything else. This is why tau physics is a reconstruction problem, not a direct observation problem, and why it rewards patience. You rebuild the parent from partial information and test whether the pattern fits. The tau is a puzzle where the missing pieces are not lost, but fundamentally unmeasurable on an event-by-event basis. The best you can do is constrain them statistically, and then ask whether the constraints align with the tau. The standard model predicts the tau's couplings to W and Z match the electron and muon. The only allowed differences come from mass, phase space, and detector acceptance. That statement is called lepton universality, and it is one of the model's most stringent promises. It is also a promise that can be tested in several independent ways, which is why it becomes a recurring checkpoint. Universality sounds simple, but the tau makes it operationally difficult, and difficulty is where mistakes can hide. Because the tau decays before it can be tracked as a stable particle, the measurement is always indirect, filtered through decay products and reconstruction choices. The physics is clean, yet the experimental path is complicated. That contrast, simple theory, messy signature, creates a tension that runs through every tau result. Tau decays split into two broad classes that drive every analysis, and the split is both physical and practical. Leptonic decays produce an electron or muon plus neutrinos. Hadronic decays produce pions and kaons plus a tau neutrino. This division is practical because it maps directly onto what detectors can identify, and it maps onto different backgrounds. In leptonic decays, the visible lepton is clean, but the neutrinos smear the energy spectrum. The charged lepton carries only a fraction of the tau's energy, and that fraction varies widely from event to event. The event shows a prompt lepton with missing transverse energy aligned imperfectly. Even the lepton's isolation can be misleading, because the invisible momentum can make the event look simpler than it truly is. That imperfect alignment is a clue with a subtle origin, rooted in three-body kinematics and spin. In T, N or T, MEMD, the neutrinos share momentum in a three-body decay, so the visible lepton is not locked to a single direction. Even when the tau is boosted, the missing momentum does not point exactly along the lepton. The tau's polarization, inherited from its production, also shapes these angular distributions in measurable ways. In hadronic decays, the tau often makes a narrow jet with 1 or 3 charged tracks, and that low multiplicity is a signature. Neutral pions add photons in the electromagnetic calorimeter, forming a compact cluster. Many of these decays proceed through intermediate resonances, like the R or A1, which imprint characteristic masses and angular patterns. Those resonances are not decorative details. They are the strong interaction organizing the hadronic final state into recognizable structures. A one-pronged decay might be as simple as a single charged pion plus a neutrino, and it often looks like a lone track with a compact calorimeter deposit. A three-pronged decay often forms a tiny secondary vertex, where 3 tracks emerge from a point slightly displaced from the collision. In both cases, the tau's neutrino steals energy, leaving the visible system lighter than the parent. That missing energy is not a nuisance alone, it is part of the tau's fingerprint. Detectors separate these possibilities using layered evidence because no single subsystem is sufficient. The inner tracker measures charge tracks and impact parameters. Calorimeters measure energy deposits and shower shapes. Each subsystem offers a partial view, and the tau is recognized when those views agree. The most convincing tau candidates are the ones where every layer tells the same story, with no contradictions. In a modern detector, the tracker is the first storyteller, and it speaks in micrometers. Silicon layers close to the beam pipe record hits with micrometer precision, allowing the reconstruction of track curvature and origin. A tau that lives long enough to move even tens of micrometers can leave a measurable deviation from the primary vertex. That deviation is not dramatic in an image, but it is dramatic in statistics. Calorimeters add a second, more visceral picture, because they turn invisible energy into light and electronics. Electromagnetic showers from electrons and photons spread in a characteristic way, while hadronic showers are rougher and more variable. A hadronic tau often leaves a compact deposit, with an electromagnetic component from P0, Gg sitting inside the hadronic energy. In finely segmented calorimeters, that P0 component can appear as 2 nearby photon clusters that almost merge. Muon systems tag penetrating tracks, and electron identification uses matching between tracks and electromagnetic clusters. Tau identification uses isolation, low multiplicity and collimation, and it often uses multivariate classifiers trained on known samples. The idea of isolation is simple in plain language. A real tau tends to be lonely, while a jet tends to have company. In practice, lonely must be quantified with cones, thresholds, and pile-up corrections. At hadron colliders, tau reconstruction is harder because jets are everywhere, and the collision is never quiet. A quark or gluon jet can mimic a hadronic tau, so algorithms focus on narrowness and track counting. They also examine how energy is distributed radially, because tau jets are typically tighter than QCD jets. Substructure variables, how the energy is layered within the jet, become a way to separate a tau's disciplined decay from a jet's chaotic fragmentation. The environment at the LHC adds another complication. pileup, the overlay of many collisions in one crossing. Many proton collisions occur in the same bunch crossing, sprinkling extra tracks and energy across the detector. A tau candidate must be separated from that clutter, or it will be misidentified, or its energy will be mismeasured. Even the primary vertex assignment matters, because a tau's tracks must be connected to the correct collision point. Missing transverse energy becomes central at the LHC, because neutrinos are common in tau decays and in many backgrounds. Analysts use momentum imbalance in the plane transverse to the beams. Since the initial transverse momentum is near zero, any imbalance points to invisible particles or to measurement errors. The missing energy vector is therefore both a clue and a liability, and it must be treated with skepticism. But missing energy is also fragile, because it depends on calibrating every other object in the event. Mismeasured jets, pile-up collisions and detector cracks can fake imbalance. Even small biases in jet energy scale can create apparent neutrino-like signatures when multiplied across busy events. The tau's invisibles are real, yet the detector can manufacture invisibles of its own, so tau analyses lean on redundancy, combining multiple observables into discriminants that can be validated. They also use control samples where taus are expected to validate efficiencies and backgrounds. A z-TT sample, for example, becomes a calibration laboratory for tau identification in real collision conditions. In that laboratory, analysts check whether the reconstructed tau properties match the well-known z mass and production rates. The tau's brief life also creates a geometric handle, and geometry is often more robust than energy. Some decays produce a measurable impact parameter or a secondary vertex, especially in three-prong modes. The displacement is small, but it is coherent, and it scales with the tau's boost in a predictable way. That scaling lets analysts distinguish a genuine lifetime effect from random misreconstruction. That displacement is tiny, but it is statistically powerful across many events. It distinguishes taus from prompt jets, and it anchors the idea that the parent was short-lived. In event displays, it appears as a slight offset, tracks that do not quite point back to the luminous center. The offset is a whisper in a single event, yet it becomes a chorus when thousands of events are combined. Once the tau existed, the question shifted from discovery to consistency, and consistency is where the standard model is most vulnerable. Does the tau obey lepton universality, or does the third generation hide extra interactions? The tau is where the standard model's symmetry claims meet the messy reality of heavy mass and rapid decay. If a deviation appears here, it is harder to dismiss as a fluke of statistics alone. Universality can be tested in W decays, comparing W to N, Mn, and Tion rates. In the standard model, the coupling is the same, but the tau mass changes kinematics. The W does not prefer one lepton, yet the detector might, because the visible signatures differ. The tau's neutrinos and hadronic modes force the experiment to compare unlike with unlike, and that comparison must be carefully normalized. The tau's mass reduces phase space slightly and reshapes decay product spectra. That complicates acceptance, because triggers and selections respond differently to softer visible objects. A tau that decays hadronically may fail an electron trigger, and a leptonic tau decay may look like an ordinary prompt lepton with extra missing energy. Even the same decay can look different depending on whether the tau is produced centrally or forward, where detector coverage changes. Even the concept of rate becomes layered, because a measured rate is never raw. The experiment measures a rate after selections, corrections, and background subtraction, and then unfolds back to a physical branching fraction. Each step is a chance for the tau's complexity to masquerade as a deviation from universality. The discipline is to treat every correction as a hypothesis that must be stress-tested, not as a mere technicality. Z decays offer another audit, because Z to E plus Z, M plus M, and T plus Z can be compared with high precision. At an electron-positron collider, the environment is clean enough for precision. The Z resonance is also a gift. It produces leptons copiously, with well-understood kinematics. When the Z is produced at rest in the lab frame, the event geometry becomes almost textbook, and deviations stand out. At CERN's LEP, Z bosons were produced in enormous numbers at the Z pole, and the Z line shape was mapped with care. The measured partial widths to charged leptons tested universality at the per-mille level. Those measurements were not only about the tau, They were about whether the electro-weak theory held together under scrutiny. The Z's couplings encode the structure of the weak neutral current, so every decimal place mattered. LEP's detectors, Aleph, Delphi, L3, and Opal, turned event reconstruction into an art of precision, and they did it with complementary designs. They tracked leptons with exquisite resolution, measured energies with carefully calibrated calorimeters, and compared results across experiments to control systematic errors. In that setting, the tau's messiness became a controlled variable rather than a fatal flaw. The collaborations also developed common language for uncertainties, so that differences could be traced rather than argued. LEP also measured the Z's invisible width, which counts light neutrino species. The result pointed to 3 active neutrinos, matching 3 charged lepton families. The method is elegant. Measure the total Z width, subtract the visible decay widths, and the remainder is the invisible contribution. In the plots, that invisible width is not a shadowy guess. It is a clean residual, a number extracted from the Z's sharp resonance profile. That count is a crucial narrative hinge, because it makes 3 generations look like a closed set. The ledger seems to stop at 3, yet it never explains why. If there were a 4th light neutrino, the Z would have decayed invisibly more often, and LEP would have seen it. The absence becomes information, and the information becomes a boundary around what the standard model can hide. The implication is both satisfying and provocative, because closure can feel like an answer even when it is not. The standard model appears complete in its family structure, but completeness is not the same as understanding. Why should the universe choose exactly 3, and why should the 3rd be so heavy? When a pattern is repeated 3 times, you begin to wonder whether it is a rule or a clue. At the LHC, the tau is both a background and a signal channel, and sometimes it is both in the same analysis. Higgs to tau-tau is a flagship measurement because it probes the Higgs coupling to leptons. It is one of the few ways to watch the Higgs interact with fermions directly, rather than through gauge bosons. In a sense, it is a test of whether the Higgs field truly talks to leptons the way the theory claims. The Higgs coupling is proportional to mass in the standard model, so the tau should couple far more strongly than the muon. Measuring that coupling tests the Yukawa pattern directly. It also tests whether the Higgs field is truly responsible for the tau's mass, rather than merely correlated with it. The tau is heavy enough that the signal is measurable, yet light enough that the decay is still common. In practice, Higgs TT is a reconstruction challenge layered on top of another reconstruction challenge. Each tau decay contains at least 1 neutrino, so the Higgs mass cannot be reconstructed from visible products alone. Analysts use specialized algorithms that combine missing transverse energy with tau directions to estimate the parent mass. Some methods assume the neutrinos are roughly collinear with the visible decay products when the taus are boosted, and then solve for consistent momentum fractions. Visually, the Higgs signal is not a single dramatic peak at first glance, and that is part of its character. It is a small excess extracted from distributions, where backgrounds from Z, TT and misidentified jets must be modelled with care. The tau is a subtle messenger, and the Higgs must be teased out of its whisper. In the final plots, the discovery is a gentle rise above expectation, and the significance comes from the stability of that rise across categories. Any deviation in Higgs to tau-tau could indicate modified Yukawas or mixing with new scalars. 3rd-generation couplings are a natural place for such effects to hide. If new physics scales with mass, the tau becomes an early warning system. The question is always the same: is the excess a new interaction, or a mismodelled background wearing a convincing mask? The tau also appears in searches for heavy resonances that decay to tau pairs. New Z-prime bosons or leptoquarks could prefer the 3rd generation, evading lighter lepton constraints. In those searches, the tau's difficulty is the price paid for access to otherwise hidden possibilities. The event displays can look deceptively ordinary. 2 narrow tau candidates, missing energy, and little else. Yet the invariant mass estimators can reach into the multi-TV regime. This is where universality becomes a stress test rather than a slogan. If new physics couples by mass or by flavour, it might show up first into final states. The 3rd generation is heavy, and heaviness often invites stronger couplings in speculative frameworks. But the same heaviness also invites experimental bias, because heavy objects are reconstructed through complex decay chains. Yet the tau is difficult, and difficulty can masquerade as anomaly, especially when statistics are limited. Detector effects, misidentification, and modelling of hadronic tau decays can bias measured rates. A small mismatch in fake rates can look like a new interaction if it is not controlled. The discipline is to treat every anomaly as a question about both nature and method. So every universality claim must separate physics from instrumentation, and that separation is never automatic. Analysts compare channels, propagate efficiencies, and cross-check with processes where theory is clean. They also perform closure tests, asking whether the analysis reproduces known signals before it is trusted to reveal unknown ones. A good tau analysis is therefore as much about proving reliability as it is about extracting a number. Beyond universality lies a sharper kind of tension, built from forbidden processes. The standard model has selection rules that make certain decays essentially impossible. These are not merely rare by accident, they are suppressed by the structure of the theory. When you search for them, you are searching for cracks in the rules themselves. Lepton flavor violation in charged leptons is one of the cleanest examples, because it is conceptually simple and experimentally crisp. A decay like TIMG changes flavor without neutrinos in the final state. It would mean that a tau can turn into a muon and a photon directly, violating the separate conservation of tau and muon number. In a detector, it would look like a two-body decay with a sharp energy relationship, almost like a signature drawn with a ruler. In the minimal standard model with neutrino masses, such decays can occur via loops, because neutrino mixing allows flavors to communicate indirectly. But the rates are unimaginably tiny, far beyond any realistic experimental reach. The suppression comes from the smallness of neutrino masses and the way flavors mix, which makes the loop contributions cancel almost perfectly. The predicted branching fractions are so small that 0 is a good approximation for any experiment we can build today. That tiny prediction is the point, because it turns any observation into a clear signal. If TMing is seen, it is not a small correction. It is new physics made visible. The moment such a decay appears, the standard model is no longer the full story. The discovery would not be an incremental update, it would be a structural failure of the old selection rules. The same logic applies to MEG, M through E, and muon conversion in nuclei. Those processes probe different combinations of couplings and energy scales. Together they form a network of constraints that can point toward, or fence in, theories beyond the standard model. The tau's role is complementary, because it tests the third generation directly, rather than extrapolating from lighter flavors. The tau complements the muon because it has more available decay channels, and because its heavy mass opens more theoretical doors. Its large mass allows many hadronic final states and more phase space for exotic mediators. If a new particle couples preferentially to heavy flavors, the tau may be the first charged lepton to reveal it. That possibility is why tau flavor violation remains compelling even when muon limits are extraordinarily tight. Experiments therefore search for T3M, TM plus mesons, and TE plus photons. Each mode tests whether flavor is truly conserved in charged lepton interactions. Some searches look for clean, fully reconstructed final states, while others exploit distinctive resonance structures in hadronic products. In each case, the goal is to reduce the tau's usual missing energy ambiguity, because many LFV targets contain no neutrinos at all. These searches are also a bridge between colliders and dedicated flavor factories, and the bridge is built from statistics. Electron, positron machines produce huge numbers of taus with clean event structure. Their advantage is clarity, fewer overlapping interactions, and a well-defined initial energy. In that environment, the event can be divided into hemispheres, and one hemisphere can be used as a tag that confirms a tau was present. At colliders like the LHC, taus are produced in heavy flavor decays and electroweak processes, but the environment is busy. At B factories, tau pairs are produced copiously with lower backgrounds, and the event topology is simpler. In both cases, the goal is the same, but the experimental tactics differ. The LHC leans on sophisticated object identification and missing energy reconstruction, while flavor factories lean on kinematic closure and cleanliness. Across these platforms, the method is consistent, and it is almost ritualistic in its steps. Identify a tau candidate, reconstruct its visible products, and look for a forbidden combination with no missing energy. The absence of neutrinos in many LFV targets is a feature, because it sharpens kinematics. It turns the tau from a puzzle with missing pieces into a puzzle that should close perfectly. A true LFV decay would peak at the tau mass with balanced momentum. In a clean E+cis environment, the signal would look almost too perfect. The decay products alone would account for the tau's energy, and the event would close without invisible escape. That is why these searches can be so decisive. The background tends to smear, while the signal would concentrate, and the difference is visible in the shape of the distribution. Non-observation sets limits that translate into constraints on new physics scales, and those constraints can be surprisingly high. Those limits often reach far beyond direct production, because loops can feel very heavy particles. Even if a new mediator is too massive to create in a collider, it can still leave a fingerprint in a forbidden decay. In this way, the tau becomes a kind of antenna for physics that is otherwise out of reach. The tau also invites a deeper question about why the third generation is heavy across the board. The top quark is extremely heavy, the bottom is heavier than lighter quarks, and the tau is heavier than its siblings. The pattern looks deliberate, as if the third generation sits closer to the mechanism that sets mass. If mass is a message, the third generation seems to be written in bold. In the standard model, that heaviness is encoded in Yukawa couplings, which are the particle's direct link to the Higgs field. The tau Yukawa is much larger than the muons, and the muons is much larger than the electrons. These couplings are simply parameters in the theory, measured rather than predicted. They are inputs, not outputs, and that is why they feel like unfinished business. The model accepts these numbers but does not derive them, and that gap has a name. This is the flavor problem, the hierarchy of masses and mixings that looks patterned but unexplained. It is one of the reasons the standard model feels both complete and incomplete at the same time. The equations work, yet the values feel like they came from somewhere else. A common suspicion is that the third generation is closer to the mechanism that sets masses, even if we do not yet see that mechanism directly. If new dynamics generate Yukawas, they might couple most strongly to the heaviest fields. That suspicion is not proof, but it is a guiding intuition that shapes how physicists prioritize searches. It is also why the tau, despite being difficult, remains strategically important. That idea shows up in many beyond standard model frameworks that are already hinted at by the tau's role. Some introduce new Higgs-like scalars, some introduce flavor symmetries, and some introduce compositeness. The tau becomes a practical probe of those ideas because it is heavy enough to be sensitive, but light enough to be produced in huge samples. It is a rare combination in particle physics, where heaviness often comes with scarcity. It also sits at the boundary between pure lepton behavior and hadronic complexity, and that boundary is scientifically rich. Its hadronic decays involve resonances and form factors, which test QCD in a controlled weak process. The weak interaction sets the overall structure, while the strong interaction shapes the hadronic final state. In other words, the tau provides a laboratory where the electro-weak theory hands QCD a well-defined initial state. That boundary creates both opportunity and uncertainty, and both must be acknowledged. Hadronic tau decays can constrain the strong interaction at low energies, and they can be used to test conserved vector current ideas and spectral functions. They also complicate precision tests with modelling dependence. When the hadronic current is not perfectly known, theory predictions carry their own subtle error bars, and those error bars must be carried honestly into universality tests. Still, the tau's role in the story is not to tidy the ledger. It is to deepen the mystery of repetition, because nature did not stop at 2 copies. The tau looks like an electron under forces, yet it carries a much larger mass and a much shorter life. It is familiar in charge and spin, yet alien in consequence. 3 generations are not just an aesthetic choice, because they shape what is possible in the early universe, where temperature sets the cast. At high temperatures, taus were abundant and in equilibrium with the plasma. In that hot, dense era, reactions happened faster than the universe expanded, and particles appeared and disappeared in a constant churn. The tau was not exotic then. It was ordinary, because the thermal energy could pay its mass. As the universe cooled below the tau mass, taus annihilated and decayed, dumping entropy into lighter species. That timing affects how energy is partitioned among photons and neutrinos. In plain terms, when a heavy species disappears, it reheats what remains, and the details matter. The tau's disappearance is therefore part of the universe's thermal bookkeeping, even if it leaves no direct relic today. If the third generation has extra interactions, those interactions could change freeze-out histories, and Cosmology would notice the difference. They could alter neutrino decoupling or modify the effective number of relativistic species. Cosmology becomes an indirect detector, sensitive to energy flow even when individual particles are long gone. The question is not whether we can see Taus in the sky today, but whether the early universe kept their secrets in its expansion history. More provocatively, new third-generation couplings could feed the matter-antimatter story. If they introduced new CP violating phases, they could help generate a lepton asymmetry. The tau itself would be gone, but the asymmetry could remain as a fossil of microscopic imbalance. That possibility turns tau physics into a conversation with cosmology, where the evidence is not a track but a cosmic ratio. That lepton asymmetry could be partially converted into baryon asymmetry by electro-weak sphalerons. The mechanism is subtle, but the narrative is clear. Early universe processes can transform a preference in leptons into a preference in baryons. The question is whether the third generation carries extra ingredients that make such a preference easier to create. If it does, then the Tau's family is not redundant, it is consequential. So Tau physics is not only about a particle that dies quickly, it is about whether the third generation is a portal to the origin of mass and the origin of cosmic imbalance. The Tau's brief existence becomes a test of ideas that reach far beyond the detector hall. It is a short-lived particle with long-lived implications. CERN's role threads through this chapter as both precision and energy frontier, and that duality is part of the institution's scientific identity. LEP measured Z properties with extraordinary accuracy, fixing the count of light neutrinos. Its legacy is a set of numbers so tight that any deviation today must fight against decades of consistency. Those numbers are not merely historical, they are constraints that still shape how new results are interpreted. The LHC then pushed to higher energies, producing Taus in Higgs decays, electro-weak processes, and heavy flavor cascades. Together, they test the same couplings in different regimes. One machine weighs the theory with fine scales, the other strikes it with force. When both approaches converge, the theory looks not just successful, but strangely durable. Precision and energy are complementary because they fail in different ways, and that difference is useful. Precision can reveal tiny deviations without producing new particles. Energy can produce new states directly if they are accessible. When both approaches agree, the standard model looks unreasonably resilient. When they disagree, the disagreement becomes a map of where to dig. The Tau sits at the intersection of those strategies, because it is both a precision object and a high-energy final state. It is hard to measure, but it is hard to ignore. It keeps returning in universality tests, in Higgs decays, and in the quiet searches for forbidden transitions. Each return feels like a reminder that the third generation is not a footnote. By the end of the chapter, the Tau leaves a specific impression, and it is an impression made of contradictions. It behaves like an electron under forces, yet it carries a much larger mass and a much shorter life. Its decays are violent in the detector's language, sudden sprays of tracks and clusters, yet they follow rules with remarkable regularity. The violence is not randomness. It is structured fragmentation governed by the weak interaction. That combination makes the third generation feel less like redundancy and more like a coded message. The standard model can describe the Tau's decays in detail, but it cannot explain why the Tau exists. We can calculate branching fractions, angular distributions, and cross-sections, and still not answer the simplest question. At some point, precision becomes a kind of pressure, pushing on the theory's unexplained parameters. Why 3? Why this hierarchy? Why a particle that lives for 1/10 of a trillionth of a second, yet shapes how we test the deepest symmetries? The Tau does not merely add a line to the particle table, it adds a question mark. And because it is heavy, that question mark is written with extra ink, and the Tau is still the simpler sibling in its own family. The charged leptons are strange enough, but the neutrino is stranger still. The next chapter follows the particle that changes flavor as it travels, and rewrites what a family even means. The Tau made 3 charged leptons feel like a deliberate pattern, not an accident, because each one carries the same charge and spin. Their differences look like a simple hierarchy of mass, as if nature repeated a template and adjusted only the weight. The neutrino makes that pattern unstable, because the family labels can change, and the change is written into quantum mechanics. Neutrinos are everywhere. even when nothing else seems to be there, and that claim is not poetic exaggeration. They stream from the sun, from reactors, from accelerators, and from the deaths of stars, crossing space with almost no resistance. Even inside this room, a constant flux passes through, indifferent to walls, skin, and stone. Start with the biggest claim, because it reframes scale and importance in a single step. Neutrinos may be the most numerous matter particles in the universe, outnumbering atoms by orders of magnitude, and they do it quietly, without leaving tracks. If you could suddenly see them, the emptiness between galaxies would look crowded, and the idea of vacuum would feel incomplete. Visually, imagine a night sky that looks empty, then overlay it with invisible rain, trillions of particles passing through every square centimetre each second. The air, the walls, and your own body are not barriers in any ordinary sense. They are simply places where a neutrino almost never decides to interact, because the weak force rarely makes the connection. The early universe produced neutrinos in enormous numbers, then let them slip away as the cosmic fireball expanded. When the cosmos was seconds old, neutrinos decoupled from the hot plasma and began free streaming, because the weak interaction became too slow. That moment is easy to say quickly, yet it marks a permanent separation in the universe's thermal history. Decoupling is a timing argument, and it is surprisingly concrete. At very high temperatures, collisions happen so frequently that particles stay in thermal contact, sharing energy like a crowded room shares heat. As the universe cools and thins, the interaction rate drops below the expansion rate. Then the neutrinos effectively stop talking to everything else. From that point on, their momenta mostly redshift with the universe, like a sound that stretches into a lower note. Those relic neutrinos should still fill space today as a cosmic background, as real as the microwave background but far more elusive. They're colder than the microwave background, harder to detect, and still a major part of the universe's particle inventory. In principle, every cubic centimetre of space contains hundreds of them, drifting through the Milky Way as a faint ancient wind. The temperature difference is not a footnote, because it encodes a historical event. After neutrinos decoupled, electrons and positrons annihilated and heated the photons, while the neutrinos kept cooling with expansion. The result is a neutrino background that is predicted to be about 1.95 Kelvin, colder than the 2.7 Kelvin glow of the CMB. That number is a fossil, a thermodynamic receipt from the first seconds. Even without direct detection, their existence is a robust prediction of the same thermal history that explains light elements. Big Bang nucleosynthesis and the cosmic microwave background both carry neutrino fingerprints, because neutrinos affect the expansion rate during the first minutes. When cosmologists fit helium and deuterium abundances, they're also testing how much invisible radiation the early universe carried. In that early era, the universe was a nuclear reactor with no walls, and timing mattered more than chemistry. The faster the universe expanded, the earlier neutrons froze out of equilibrium, and the more helium would eventually form. Neutrinos contribute to that expansion, so their abundance leaves a measurable imprint. This is why a particle that barely interacts today still mattered. Gravitationally, when the universe was dense and young, neutrinos also arrive from the sun in a steady, nuclear-powered beam that never switches off. Every fusion reaction that turns protons into helium produces electron neutrinos as part of the weak process, because a proton must become a neutron to build deuterium. The sun's light takes thousands of years to random walk outward, but the neutrinos leave immediately, carrying a real-time report from the core. The key step is the proton chain, and it is weak interaction limited. Two protons collide, but one of them must transform, emitting a positron and an electron neutrino. That conversion is rare for any given pair, yet the sun has so many protons that the total neutrino output is enormous. In a sense, the sun shines because the weak force allows it to shine slowly, keeping the core stable for billions of years. For visuals, the sun's bright surface fades, and we dive beneath it into a dense, glowing core. There, in a region smaller than a quarter of the sun's radius, fusion reactions flicker like microscopic sparks. From each spark, a neutrino shoots outward almost instantly, escaping long before any photon can fight its way out. The neutrino's path is nearly straight, while light ricochets through plasma like a trapped animal. Supernovae add a more dramatic source, because collapse releases gravitational binding energy mostly as neutrinos. In a core collapse supernova, Neutrinos carry away almost all the energy in a brief burst, and that burst is the true heartbeat of the explosion. The visible fireworks are the echo, delayed by expanding debris and radiative diffusion. When a massive star's iron core collapses, matter is squeezed to nuclear density, and the physics becomes extreme. Electrons are forced into protons, creating neutrons and electron neutrinos in a process called neutronization. For a moment, the core is opaque even to neutrinos, and then it becomes transparent enough for them to pour out. In that transition, the star's interior briefly resembles a neutrino furnace, hotter and denser than anything we can build. That burst is not a detail. It is the mechanism that lets the star explode in the first place. Neutrino heating helps drive the shock, and the neutrino signal arrives before light escapes, because photons must wait for the debris to thin. The shock can stall, then revive, and neutrinos provide the energy transfer that makes the difference between collapse and explosion. Historically, this became more than a theory in 1987, when detectors saw a handful of neutrinos from supernova 1987A. The count was small, but the implication was huge. A few dozen events, spread across underground tanks, confirmed that the collapse energy really does leave as neutrinos. It was also a timing triumph, because those neutrinos arrived hours before the supernova's brightening was widely reported. So neutrinos are cosmic messengers, but they are also nearly invisible to us, and that invisibility is built into their properties. They have no electric charge, they feel no strong force, and they interact only through the weak interaction and gravity, which makes them hard to stop. Their very usefulness as messengers comes from that refusal to be scattered and absorbed. That weak interaction is the reason they are called ghost particles, and the nickname is earned. A neutrino can pass through the Earth as if the planet were not there, because the probability of interaction is so small at typical energies. Only at very high energies does the Earth begin to look less transparent, and even then it is more filter than wall. Put a number on that intuition, because scale is the point. For many neutrinos, the mean free path through solid matter is measured in light years, not kilometers. The Earth is thick to us, but to a neutrino it is often a thin mist. The cross-section grows with energy, yet at solar energies it remains so tiny that detection becomes a statistical art. Explain the interaction in one accessible step, without hiding the physics that makes it possible. Neutrinos scatter by exchanging W and Z bosons, which means they can create charged leptons or recoil nuclei. The mediators are heavy, so the interaction is short-range and suppressed at low energies. In plain terms, the weak force is weak because its messengers are massive, and massive messengers do not travel far. Charged current interactions use the W boson and produce a charged lepton that matches the neutrino flavor. Neutral current interactions use the Z boson and leave the neutrino a neutrino, while still kicking energy into the target. In both cases, the neutrino itself remains unseen, and only the aftermath is visible. What the detector records is a secondary particle, a flash of light, or a recoil that betrays an invisible visitor. This is why detection is hard, and also why it is possible at all, if you are patient and clever. You cannot see the neutrino directly, but you can see the rare debris when it finally hits something. The detector is not a net that catches neutrinos, but a camera waiting for a flash. The design philosophy is almost photographic, except the exposure times are measured in years. Detection therefore becomes an exercise in scale and patience, and it also becomes an exercise in humility. If interactions are rare, you build detectors that are massive, quiet, and shielded from ordinary backgrounds. You accept that most of what passes through will never leave a mark. Then you learn to treat every recorded photon as a clue, and every unwanted background as an adversary. Underground placement is not aesthetic. It is survival for the signal. Rock above the detector blocks cosmic ray muons that would otherwise mimic or drown the neutrino signal. Without that shielding, the detector would be a storm of false events. Even underground, experiments must fight radioactivity in the rock, in the detector materials, and sometimes even in the air. Visually, we descend into a mine shaft past dripping rock and steel supports, into a cavern carved like a cathedral. A vast tank waits in the dark, lined with photo-multiplier tubes like black eyes. In the silence, the experiment listens for light that should not be there. Every cable and scaffold looks industrial, yet the goal is almost philosophical: to make the invisible accountable. Introduce the main detector ideas as ways to turn nothing into something, because each design is an answer to the same problem. Cherenkov detectors use large volumes of water or ice to catch blue light from fast-charged particles. They trade density for clarity, letting light travel long distances to sensors. The medium must be extraordinarily pure, because scattering and absorption would erase the timing patterns that carry information. When a neutrino interaction produces an electron or muon, that lepton can move faster than light travels in the medium. The result is a cone of Cherenkov light that sensors can time and map, turning geometry into a reconstruction of direction and energy. The effect is like a sonic boom in light, a coherent shockwave of photons that draws a ring on the detector wall. The visual signature is striking, and it is also diagnostic. A muon draws a clean ring, while an electron showers and blurs the ring into a fuzzy edge. From that difference, experiments can separate flavors and reduce backgrounds. With enough events, the statistics become a kind of imaging, where probability patterns stand in for individual tracks. Scintillator detectors use organic liquids or solids that flash when charged particles deposit energy, producing a bright prompt signal. The light yield can be high, enabling low-energy neutrino detection with careful background control. They often add wavelength shifters and purification systems to keep the medium optically clean. The result is less like a ring and more like a timed pulse, a burst whose shape and coincidence can reveal what happened. Some experiments use heavy nuclei as targets to amplify interaction probability, because more nucleons mean a larger cross-section. Others use segmented detectors to reconstruct tracks and distinguish electrons from muons, and to identify neutrons that tag certain reactions. A neutron capture can add a delayed flash, giving the event a two-step signature that helps separate signal from noise. Across all designs, the logic is consistent and brutal, and it shapes the architecture of the field. You need huge mass for enough targets, extreme cleanliness for low backgrounds, and long exposure for statistics. In practice, that means years of data taking and constant calibration. It also means that the most important discoveries can be built from a small number of rare events, if those events are understood with confidence. Calibration itself becomes a quiet drama. Experiments deploy radioactive sources, lasers, and cosmic muons to map detector response, because a tiny systematic bias can masquerade as new physics. The goal is not just to see events, but to trust what they mean. Every gain drift, every timing offset, and every optical imperfection becomes part of the scientific narrative. This is where the neutrino story becomes a turning point in the documentary's central question, because the pattern of copies starts to wobble. The charged leptons look like copies, but at least their identities were stable. An electron stays an electron, and a muon does not drift into a tau. With neutrinos, the universe refuses to keep the labels glued to the particle. Neutrinos refuse that stability, and the refusal is not a minor correction to an otherwise tidy picture. A neutrino created as one flavor can later be detected as another flavor, as if the label were a temporary costume. The deeper shock is that the costume change is predictable, and it depends on distance, energy, and the medium traveled through. State the plot twist plainly, then build intuition from the ground up. Electron neutrinos, muon neutrinos, and tau neutrinos are not fixed particles in the way the electron is. They are flavor states, and flavor is defined by interaction, not by an intrinsic mass identity. The names are operational, which means they are tied to what the weak force does at the moment of detection. They are flavor states, defined by how they interact in charged current processes, and that definition is operational. The detector labels them by the charged lepton produced, not by a permanent internal tag. In other words, electron neutrino means the neutrino that makes an electron when it hits. If the same travelling state later makes a muon, the label changes, even though the particle never stopped being a neutrino. The key observation is neutrino oscillation, and it is a quantum interference effect that only appears because nature is wave-like. As neutrinos travel, the probability of each flavour changes with distance and energy, producing patterns that can be measured like fringes. The oscillation length can be kilometres, or thousands of kilometres, depending on energy and on which mass difference dominates. Give the intuitive quantum explanation without heavy math, but keep the logic intact. The neutrino produced in a weak interaction is a superposition of mass states, and those mass states propagate with different phases. The phases depend on energy and on the tiny differences between the masses. Because the masses are not equal, the waves do not stay locked, and the mixture evolves. Because the phases evolve differently, the superposition changes over time, and the flavor composition rotates. The neutrino remains a neutrino, but the mixture of flavors shifts, so detection outcomes change. What looks like identity is really a projection of a moving quantum state. The detector asks a yes or no question, electron, muon, or tau, and quantum mechanics answers in probabilities. A useful visual is three waves sliding out of sync, almost together, then slightly apart, then recombining. The detector does not see the waves directly, but it sees the interference in the statistics. The oscillation is not a single event, but a probability rhythm. Over many detections, the rhythm becomes a map of the underlying parameters. This is the family rule that breaks, and it breaks in a controlled, measurable way that experiments can fit. The oscillation pattern depends on mass differences and mixing angles, which experiments can extract. It also depends on a possible complex phase that can introduce CP violation. In other words, oscillations are not merely a curiosity, they are a precision tool for reading hidden structure. Now connect to the historical tension that made oscillations unavoidable, because this story was forced by stubborn data. The Sun produced fewer electron neutrinos than expected, and the deficit persisted across detectors and methods. It was not a small discrepancy that could be ignored as calibration noise. For decades, it sat like a quiet accusation against either astrophysics or particle physics. The first generation of solar neutrino experiments, like the chlorine-based homestake detector, saw only a fraction of the predicted rate. For years, the question hung in the air: was the Sun misunderstood, or was the neutrino misunderstood? The answer would reshape particle physics. Historically, it also reshaped experimental culture, because it showed that a persistent anomaly can be a doorway rather than a mistake. That solar neutrino problem was not solved by tweaking the Sun, because the Sun was constrained by helioseismology and stellar physics. It was solved by accepting that neutrinos change flavor between the solar core and the Earth. The missing electron neutrinos were not missing at all, they had become something else. The resolution was elegant, yet it demanded a new ingredient. Neutrinos could not be massless. Heavy water detectors and neutral current measurements were decisive, because they could count all flavors. They showed the total neutrino flux matched solar models, while the electron-neutrino fraction was reduced. The Sun was right, and the neutrino was stranger than expected. Visually, it is the moment when a single missing number becomes three separate tallies, and the accounting finally balances. Atmospheric neutrinos provided a second independent stage, and the geometry of Earth became part of the apparatus. Cosmic rays make pions and kaons that decay into muons and muon neutrinos, and the muons later decay into electron neutrinos. That chain predicts a flavor ratio that can be tested. The experiment does not need a beam, because the sky provides one, and the Earth provides the baseline. Detectors saw a zenith angle dependence that pointed to oscillations, not detector error. Neutrinos coming through the Earth had travelled farther, and their flavor ratios shifted more. The planet became a baseline ruler, with the sky above and the rock below as two different path lengths. It is a striking thought. The Earth itself becomes a measuring tape for quantum phase. Reactor and accelerator experiments then turned oscillations into controlled measurements, moving from discovery to precision. By choosing baseline and energy, they mapped disappearance and appearance channels with increasing accuracy. The field began to measure mixing parameters the way earlier generations measured particle masses. This is also where engineering becomes destiny, because beam design and detector design determine which subtle effects can be separated. At this point, the implication must be stated as a structural failure of the minimal standard model, not a cosmetic adjustment. Oscillation requires non-zero neutrino masses, because massless neutrinos cannot accumulate relative phases. If all masses were exactly zero, the flavor mixture would not evolve. The oscillation data therefore forces a new term in the theory, whether we like the aesthetic outcome or not. The standard model as originally written had neutrinos exactly massless, and it did so for a specific reason. It included only left-handed neutrinos, and without right-handed partners, the usual Higgs mechanism cannot write a Dirac mass term. The model also conserved separate lepton family numbers, treating flavors as independent ledgers. That structure was tidy, but nature did not sign the ledger. Oscillations prove that ledger is incomplete, because the flavors mix in propagation. The model can be extended to include neutrino masses and a mixing matrix, but the origin of those masses remains unexplained. The extension works, yet it feels like a patch over a deeper gap. Why should the smallest masses belong to the particles that are hardest to catch? And why should their mixing be so bold? Emphasize the turning point in the chapter's arc because it changes what generation means. The neutrino is not just another copy, it is evidence that the copy labels are not fundamental. The generations are not sealed compartments, and the neutrino is the leak. Once the leak exists, the question becomes whether the compartments were ever truly separate. Now revisit lepton number with care, because the story becomes subtle rather than simple. In many weak interactions, total lepton number appears conserved, even though individual family numbers are not. The bookkeeping works in practice, but the categories are not as rigid as they look. It is the difference between conserving a total budget and conserving every labelled envelope inside the budget. Electron lepton number, muon lepton number, and tau lepton number are violated by oscillations, and that violation is direct. A neutrino produced with an electron can later behave as a muon neutrino, changing the bookkeeping. The universe does not respect our neat labels when quantum phases are involved. The violation is not random though, and that regularity is what makes it so powerful. Yet in the standard model's charged current interactions, the total lepton number L is still conserved in the simplest picture. Neutrino oscillation changes flavour, but it does not create net leptons from nothing. It reshuffles identities without changing the total count. That distinction matters because it tells us what kind of symmetry is being tested. That statement is true in the simplest extension, where neutrinos are Dirac particles, which mirrors how electrons behave. Dirac neutrinos have distinct antiparticles, and lepton number can remain an exact symmetry. In that case, a neutrino and an antineutrino are fundamentally different states. The open question is whether nature chose that familiar option, or a stranger one that only neutrinos can take. But the deeper question is whether neutrinos are Majorana particles, and the stakes are unusually high. A Majorana neutrino would be its own antiparticle, and that would allow processes that violate total lepton number. It would mean that lepton number is not a protected global rule. If that is true, then a symmetry we take for granted becomes a temporary convenience. Explain why this matters without diving into formalism, but do not hide the conceptual shock. If neutrinos are Majorana, then lepton number is not a fundamental conservation law, it is an approximate rule that can fail. That would place neutrinos in a special category among fermions. It would also suggest that the neutrino mass itself may come from a mechanism unlike the one that gives mass to the electron. The flagship search is neutrinoless double beta decay, and it is designed like a trap for a forbidden event. If a nucleus can emit 2 electrons without neutrinos, it would mean the neutrino can be absorbed as an antineutrino, implying Majorana mass. The signature is a sharp energy peak where ordinary decays produce a broad spectrum. The experiment is essentially asking whether the neutrino can turn around in a way no Dirac particle can. Visually, this is a different kind of underground experiment, quiet, cold, and obsessively clean. Crystals or liquid xenon sit inside nested shields, while researchers count events over years. The detector is not looking for a flash of direction, but for an energy line that should not exist. Every background line is catalogued, and every material is screened because one stray decay can imitate the signal. Non-observation sets strong constraints, but it does not close the question, because the interpretation has moving parts. Different isotopes, nuclear matrix uncertainties, and mass hierarchies leave room for discovery. A null result can mean the process is rare, or that the neutrino masses are arranged unfavourably. It is a search where silence is informative, yet never fully decisive, so neutrino physics becomes both a measurement program and a philosophical shift, because it tests what we mean by particle and antiparticle. The particle that barely interacts may decide whether a global quantum number is real or emergent. It is a quiet particle with loud consequences, and it forces a question that feels almost unfair. Why should the faintest actor carry the most radical script? Now connect oscillations to the 3-generation pattern in a new way, because the mixing itself is a fingerprint. Mixing is described by angles and phases, and the pattern of those parameters looks unlike quark mixing. Where quarks mix weakly, neutrinos mix strongly. The contrast is not just numerical, it is structural, as if the two sectors learn different rules for how families communicate. Neutrino mixing angles are large, which suggests a different organizing principle than the one that shapes the quark sector. The contrast hints that flavour may not be a single mechanism shared across all fermions. It is as if nature uses two different dialects for two parts of the same language. That observation is a clue, and it invites the suspicion that something hidden is shaping one sector more than the other. The mass scale is also bizarre, and it deepens the mystery of copies rather than resolving it. Neutrino masses are tiny compared to charged leptons, implying either extremely small Yukawa couplings or a new mass mechanism. Either option feels unnatural by the standards of the standard model. The electron is light, but the neutrino is almost weightless, and the gap demands an explanation. Introduce the seesaw idea as a narrative option, not a settled answer, because it is elegant but still hypothetical. If heavy right-handed neutrinos exist, they could make light neutrinos naturally small through mixing with very heavy states. The light mass becomes the inverse shadow of a heavy scale. The beauty of the idea is that it turns tiny into informative, because smallness becomes a trace of something enormous. Those heavy states would be invisible at low energy, but they could shape early universe history in decisive ways. The neutrino would then be a portal to physics at scales far beyond colliders. A tiny mass measured in a detector could point to particles too heavy to create directly. This is one reason neutrino physics feels like a message in a bottle, washed ashore from energies we cannot reach. Now widen to cosmology, because neutrinos are not only laboratory curiosities, and the universe itself becomes a detector. Their masses and abundances affect how structure forms, because free-streaming neutrinos erase small-scale density fluctuations. They smooth the early universe like a gentle, persistent diffusion. In maps of matter, their effect is subtle, yet it is spread across the entire sky. In the early universe, neutrinos behave like radiation, then gradually behave like matter as the universe cools and their momenta redshift. That transition changes the expansion rate and the growth of cosmic structure. It also changes when and how small density ripples can grow into galaxies. A particle that moves close to light speed cannot easily fall into gravitational wells, so it resists clustering until it slows. Cosmological data therefore constrain neutrino properties in a way no detector can, because the baseline is the entire history of the cosmos. The cosmic microwave background and large-scale structure surveys limit the sum of neutrino masses. They do it indirectly, by measuring how much clustering is suppressed. The logic is gravitational and statistical, but the conclusion reaches into particle physics. The remarkable feature is that these constraints come from patterns in the sky, not from counting particles in a tank. Temperature anisotropies, lensing maps, and galaxy distributions carry the imprint of neutrinos' reluctance to clump. The neutrinos' weak interaction becomes irrelevant, and gravity takes over as the messenger. In this regime, neutrinos are dark, not because they are mysterious, but because they are simply hard to pin down. Explain the effective number of neutrino species as a handle on hidden physics, because it compresses early universe behavior into one parameter. Neutrino decoupling sets a baseline value called n-effective, and extra relativistic species would shift it. The parameter measures radiation density beyond photons, in units calibrated to neutrinos. It's a compact way to ask whether the early universe carried more light, fast energy than we expected. Measurements of the CMB damping tail and primordial element abundances test that value with increasing precision. Deviations could indicate sterile neutrinos, dark radiation, or non-standard thermal histories. Even a small shift would imply that something else carried energy when the universe was young. The question is almost haunting. What else was present, then vanished from view? Sterile neutrinos would not interact through the weak force, but they could mix with active neutrinos, borrowing visibility through oscillations. If they exist, they would add new states to the oscillation story and new energy density to the cosmos. The word sterile would mean hidden, not irrelevant. Their existence would also sharpen the chapter's theme, because it would add new family members that refuse to be seen directly. This is where the neutrino becomes a bridge between particle physics and cosmology, and the bridge runs both ways. A parameter measured in a detector can change the inferred matter distribution across billions of light years. A pattern in the sky can constrain masses that are too small to weigh directly. The same particle is tested by underground silence and by cosmic architecture. Now raise the matter versus antimatter stakes, and connect to the documentary's conclusion theme, because the consequences may be existential. The universe contains far more matter than antimatter, and the standard model struggles to explain why. If matter and antimatter were created equally, they should have annihilated into light. The fact that anything remains is a clue that some imbalance was written into the early rules. Leptogenesis is a leading idea that uses neutrinos as the seed, and it fits naturally with the seesaw picture. If heavy neutrinos existed in the early universe, and their decays violated CP and lepton number, they could create a lepton asymmetry. That asymmetry would be a tiny preference that later becomes everything. The story is speculative, yet it is disciplined, because it connects known mechanisms to unknown parameters. Electroweak sphalerons can then convert part of that lepton asymmetry into a baryon asymmetry, because the standard model allows processes that reshuffle baryon and lepton number together at high temperatures. The result is a universe where matter survives, even if the initial conditions were symmetric. The mechanism is subtle, but the outcome is stark. It suggests that the ghost particle may have helped decide whether galaxies, stars, and observers could exist. This is not proven, but it is a coherent route from neutrino properties to cosmic outcome, and that coherence matters. It ties the smallest masses to the largest question about existence. It suggests that the ghost particle may have tipped the balance of reality. And it invites a sobering question. If neutrinos had been different by a small amount, would there be anything here to notice? CP violation in the neutrino sector becomes a key target, because it is one of the few accessible windows into that story. Oscillation probabilities can differ for neutrinos and antineutrinos if a complex phase exists in the mixing matrix. The difference is small, so experiments must be large and systematic errors must be controlled. The work is slow, because the signal is a slight tilt in a probability curve, not a dramatic new particle. Long baseline experiments compare appearance channels over hundreds of kilometers, turning geography into a precision instrument. They look for differences between neutrino and antineutrino oscillations that cannot be blamed on matter effects alone. The beam is engineered, but the question is fundamental. Visually, it is a line drawn across a map, with a source at one end and a detector waiting at the other, listening for transformations mid-flight. Matter effects themselves are part of the story, not a nuisance to subtract away. Neutrinos travelling through Earth experience different effective potentials, which can enhance or suppress oscillations and reveal mass ordering. The planet's electrons become a medium that changes the oscillation phase. In effect, Earth acts like an optical material for neutrino waves, bending probabilities rather than trajectories. The mass ordering question is another hinge, because it determines how the three mass states are arranged. We know mass differences, but we do not yet know whether the third mass state is heavier or lighter than the other two. The two possibilities, normal and inverted ordering, lead to different expectations in future searches. It is a simple either-or, yet it controls how we interpret several of the most sensitive experiments. That ordering affects predictions for neutrinoless double beta decay and for cosmological signals, so it links underground experiments to sky surveys. It also shapes how future experiments optimize baselines, energies, and detector technologies. The choice of detector is partly a choice of which unknown you want to corner. In this field, hardware decisions become theoretical bets. Now return to the family theme, because this chapter must reframe generations rather than merely add facts. Charged leptons look like stable identities with different masses, but neutrinos show that identity can be context-dependent. What you call the particle depends on how you ask the question. The family becomes less like three boxes and more like three overlapping shadows. A neutrino is defined by how it is produced and how it is detected, not by a single immutable mass. The family label is a projection, not a permanent name, and the projection changes as the state evolves. The neutrino teaches that flavor is an interaction story, not a birth certificate. That lesson is uncomfortable, because it means our categories are partly artifacts of measurement. This is the chapter's core reversal, and it lands because it is experimentally true. The standard model's family bookkeeping works for many processes, yet nature quietly violates its strictest version through oscillation. The violation is not chaotic. It is patterned, periodic, and measurable. It is the kind of violation that does not destroy a theory outright, but instead points to the missing page. So the three-generation pattern is not just repetition, it is entanglement in the broad sense of coupled quantum states. The generations talk to each other through mixing, and the mixing carries information about physics we do not yet see. The copies are not isolated, they are linked. The neutrino, by changing flavour, turns the idea of three separate families into a single connected system. The standard model can be patched to include neutrino masses, but the patch exposes deeper gaps rather than sealing them. It does not explain why the masses are so small, why the mixing is so large, or why there are three. Each added parameter feels like a clue that points beyond the model. The neutrino sector becomes the place where the standard model looks most like an approximation. That incompleteness is not philosophical. It is explicit and measurable in the data. Oscillation results force new terms in the theory, and those terms introduce new parameters and new possible symmetries. The neutrino sector becomes a map of what the standard model is missing. The map is still incomplete, but it has edges, and those edges are where discoveries tend to happen. Now connect back to the documentary's central question with a forward pull, because the narrative is about generations and their meaning. If neutrinos can change flavour, then generations are not merely copies, they are a coupled system. The question becomes not only why three, but why this pattern of coupling? Why these angles, these mass splittings, and this strange contrast with quarks? The next mystery is why the system has three components, and why their masses span such extreme ranges across the fermion families. That question now touches Higgs couplings, hidden heavy states, and early universe asymmetry. It also invites a harder observation. Maybe the pattern is telling us where to look. When a theory creaks, it often creaks at the joints, and neutrinos have already shown us one joint that moves, end with a transition that points toward anomalies and hidden sectors, keeping the tone mysterious rather than conclusive. With neutrino mass and mixing established, the story pivots to whether other precision cracks, like Muon G-2, are part of the same deeper structure. The neutrino already forced us beyond the standard model once. If the neutrino already forced us beyond the standard model once, it can do it again, and the lesson is methodological. The ghost particle becomes a guide, and the copies begin to look less like redundancy and more like a map. The next chapter follows that map into the places where the theory still creaks. Neutrinos already proved the standard model is incomplete, because flavour changes in flight. Their oscillations mean the neutrino states that interact are not the same as the states that propagate, an elegant mismatch that forces mass into the story. In practice, a neutrino is produced in a flavour state, but it travels as a superposition of mass states with slightly different phases. Over long baselines, those phases separate, and the probability of detecting each flavour oscillates with distance and energy. That single phenomenon quietly breaks the standard model's original bookkeeping, because mass terms require new ingredients or new symmetries. Now the question is whether other precision cracks point to the same hidden structure. The muon is the electron's heavier copy, and that heaviness turns it into a sensitive probe. It looks like a simple scaling of the same blueprint, yet its mass is about 207 times larger, and that single fact reshapes what it can reveal. The muon's Compton wavelength is shorter, so it samples shorter distances where heavy physics can leave a faint imprint. If new physics treats generations differently, the muon is where it can leak out. Visually, the muon feels like a familiar character wearing heavier armour. In animations, it traces the same charge track as an electron, but the curvature, timing, and decay signature tell you it is a different instrument. In a detector, it often punches through layers that stop electrons, leaving a clean, penetrating line in the outer chambers. Its lifetime is only 2.2 microseconds at rest, and that fragility makes every measurement a race against time. Start with what G means in quantum field theory, not as a number, but as a promise. A charged spin one-half particle in a magnetic field precesses, and G sets the rate. In plain language, the particle behaves like a tiny magnet, and the field tries to twist it into alignment. The precession is not a metaphorical wobble, but a well-defined rotation of the spin expectation value in time. The magnetic moment is proportional to spin, and the proportionality constant is where G enters. In classical electromagnetism, you might picture a spinning charged sphere, but in quantum theory, spin is intrinsic. There is no literal surface rotating. Even so, the equations predict a precession frequency that can be tracked like a clock hand. That clock is extraordinarily stable, which is why tiny deviations become experimentally meaningful. Dirac's simplest prediction gives G equals 2, which would be exact in a classical world. It emerges from the relativistic Dirac equation, where spin and charge are woven together by symmetry. If the vacuum were empty and interactions were absent, G would sit at 2 forever. The moment you allow the muon to interact with quantum fields, however, the value is nudged away from that ideal. Quantum fields refuse that simplicity, and the vacuum adds a small anomaly. The vacuum is not nothing. It is a restless ground state with fluctuations constrained by uncertainty and by the fields that exist. Those fluctuations distort how the muon couples to the magnetic field, and the distortion is measurable. In technical terms, the muon's electromagnetic vertex is renormalized, and the correction shows up as a shift in the form factor at zero momentum transfer. Define the observable that experiments actually quote, because the story lives in precision. The anomalous magnetic moment is m equals g-2/2. That definition is not cosmetic. It isolates the quantum correction, the part that must be computed and checked. It also makes comparisons cleaner, because the Dirac baseline is factored out, and the remaining number is small but information-rich. In a storage ring, the muon's momentum circles while its spin direction slowly slips. The difference frequency encodes AM, and it can be measured with extreme control. The motion is a choreography of two rotations, one for the orbit, one for the spin, and the beat between them is the signal. When the ring is tuned to the so-called magic momentum, certain electric field effects cancel, simplifying the interpretation. At Fermilab, the ring is a polished arena of magnets and vacuum pipes, large enough to walk inside yet tuned to parts per million. Muons enter as a polarized beam, their spins initially aligned, and they circulate thousands of times before decaying. Each decay releases a positron whose direction remembers the muon's spin at that instant. Higher energy positrons are emitted preferentially along the spin direction, so the detectors read spin precession as a rhythmic modulation in energy and time. This is not an abstract correction because it is built from measurable precession and calibrated magnetic fields. The experiment is a clock, and the muon is the hand. The magnetic field is mapped with nuclear magnetic resonance probes, and the timing is referenced to electronics that must stay stable over long runs. Even the temperature of the hall, the mechanical alignment of magnets, and subtle vibrations become characters in the story because they can shift a field map by parts per billion. The anomaly is also a microscope into the vacuum, because quantum mechanics allows temporary fluctuations. Fields can borrow energy briefly, and the muon feels their influence. What looks like empty space is a medium with polarizability, and the muon samples that medium every time it interacts. The key point is operational. The influence is not philosophical, because it changes a frequency we can measure. Use a clear metaphor that stays faithful to the math. The muon is never alone, because it is surrounded by a cloud of virtual possibilities. Those possibilities are not particles flying out to detectors, but intermediate states inside the calculation that still leave a physical imprint. You can think of them as allowable internal configurations of the fields, but keeping paths that interfere and shift the final amplitude. In Feynman diagrams, those possibilities appear as loops, where the muon emits and reabsorbs quanta. The loop shifts the magnetic moment, and the shift is calculable. A loop is a compact way to represent an integral over all allowed intermediate momenta, including very high energies. That integral is why g-2 can feel physics that no accelerator has directly produced. The first and most famous loop is purely electromagnetic. The muon emits a virtual photon and reabsorbs it, and that single diagram gives the leading correction discovered by Schwinger in 1948. The result is a divided by 2p, and it is one of the cleanest numbers in physics. Historically, it was also a triumph for the new machinery of renormalized quantum electrodynamics, because it turned infinities into a finite prediction. But the loop picture also hints at why precision becomes a telescope. The integrals do not stop at the energies we can directly create. They weight contributions from many scales, with heavier virtual particles leaving subtler but still systematic effects. The muon's anomaly is therefore sensitive to what the vacuum can briefly host. It is sensitive in a specific way, because heavy contributions decouple, but they do not vanish if couplings and chiral structure cooperate. The key scaling is why the muon matters more than the electron. Many new contributions grow roughly like the lepton mass squared. That scaling is not universal, but it's common when heavy new particles generate effective interactions suppressed by their mass. In plain terms, the muon's extra mass makes it easier for new physics to flip chirality, which is required to create a magnetic moment operator. A heavier muon couples to the same forces, but it amplifies short-distance physics. It acts like a stronger antenna for heavy virtual particles. In effective field theory language, the muon more efficiently probes higher dimension operators, because the chirality flip needed for a magnetic moment naturally brings in the lepton mass. That is why the electron's G-2 is a pristine QED laboratory, while the muons becomes a hunting ground. So G-2 becomes a precision telescope, reaching beyond collider energies without producing new states directly. It measures influence, not debris. It is the difference between seeing a planet by its reflected light and inferring it from the wobble of its star. The wobble is tiny, but it accumulates, and it can be cross-checked by independent observers. Lay out the standard model prediction in 3 pillars, because each pillar has its own uncertainties. QED dominates, electro-weak adds small corrections, and hadronic effects complicate everything. The final theory value is a sum of contributions that differ wildly in size and in calculational difficulty. The art is to keep each piece on the same footing so the combined uncertainty is honest. QED is the triumph section, built from photons and charged leptons with perturbation theory. It is computed to staggering order, and it matches reality almost perfectly. The series includes thousands of diagrams at high loop order, and the agreement across decades has made G-2 a benchmark for quantum field theory itself. The calculation is so mature that its remaining uncertainty is dominated by inputs, not by missing terms. In visual terms, QED is a clean lattice of light. Photons flicker in and out, but the rules are crisp, the coupling is small, and the expansion converges. When theorists quote uncertainties here, they are often limited by the measured value of the fine structure constant rather than by missing diagrams. It is a rare part of fundamental physics where the mathematics feels almost industrial, repeatable, checkable, and sharply convergent. Electro-weak loops add W, Z, and Higgs contributions, suppressed by their heavy masses. They are small but clean, and they are part of the baseline. These corrections were historically important, because they confirmed that the unified electroweak theory contributes in exactly the way the standard model says it should. Even before the Higgs was discovered, the structure of these loops helped validate the framework. The electroweak piece is also conceptually revealing. It shows that even particles far heavier than the muon can tug on its properties through loops, provided the interactions exist. That is the same logic new physics models rely on, except the new particles are hypothetical. The muon, in effect, carries a ledger of every field it can talk to, even if that field is too heavy to appear on shell. Hadronic contributions are the hard part because quarks live inside strongly coupled QCD at low energies. The vacuum polarization of hadrons cannot be computed as easily. At these energies, the strong coupling is large. Perturbation theory breaks down, and the vacuum behaves like a complicated resonant material. Instead of a smooth correction, you get a landscape of thresholds and resonances, dominated by states like the rho meson. One method uses E plus E minus to hadrons data to reconstruct hadronic vacuum polarization. Another uses lattice QCD to compute the same quantity from first principles. Both routes aim to determine how a photon propagator is modified when it can fluctuate into quark, antiquark states, and hadronic resonances. Conceptually, it is the same photon line in the diagram, but the interior is filled with strong interaction complexity. In the data-driven approach, experiments measure the cross-section for electron, positron, annihilation into hadrons as a function of energy. Through dispersion relations, that cross-section feeds into an integral that predicts the hadronic vacuum polarization contribution to M. It is a beautiful bridge between measurable rates and a loop correction. Visually, you can imagine a curve of cross-sections being folded into a weighted kernel, where low energies matter disproportionately because of how the integral is shaped. In lattice QCD, the bridge is different. Space and time are discretized into a grid, quarks and gluons are simulated numerically, and correlation functions are computed to extract the needed polarization. The method is conceptually direct, but it is technically demanding, because finite volume, lattice spacing, and quark mass tuning all matter. Even the choice of boundary conditions and the handling of long-distance tails can shift the result, so collaborations run ensembles for years to tighten errors. These approaches do not always agree within claimed errors, and that disagreement is part of the tension. The anomaly is partly a physics question, and partly a calculation question. When two careful methods diverge, The field has to ask whether uncertainties were underestimated or whether subtle effects were missed. It is a reminder that precision is not only about more digits, but about correctly accounting for what can bias them. Explain hadronic light-by-light scattering as a second difficult piece, because it is smaller but subtle. A loop of hadronic structure couples to multiple photons and shifts AM. Here, the muon effectively interacts with a complex hadronic blob through several photon lines, and the internal structure cannot be reduced to a single measured cross-section. The difficulty is that the photons are off-shell, probing internal hadron structure in configurations that experiments do not directly isolate. Hadronic light-by-light is also where intuition can fail. The contribution depends on how hadronic excitations, like pions and heavier resonances, couple to photons in off-shell configurations that are not directly accessible in a simple experiment. Lattice calculations and model-based approaches have both improved, yet the uncertainty remains a limiting factor. The progress is real, but it is incremental, and each reduction in error requires new theoretical control rather than mere repetition. Now state the experimental situation as an investigative thread, not as a verdict. Brookhaven measured M with a persistent offset from standard model expectations. The E821 experiment became a landmark because it pushed control of systematics to an extraordinary level and still found a result that did not sit comfortably. That offset was not a dramatic mismatch, but it was consistent across runs, which is exactly the pattern that keeps physicists awake. Fermilab repeated the measurement with improved control and confirmed the same direction of deviation. The combined result sharpened the question rather than closing it. The statistical power increased, and the experimental techniques were refined, but the central value continued to suggest something extra. In the background, teams also improved beam delivery, detector segmentation, and calibration strategies to ensure the oscillation signal could not be faked by mundane effects. In the visuals, the storage ring becomes a stage for a slow, relentless drift. The spin precession signal appears as an oscillation in detected positron counts, a wave whose frequency can be extracted with careful fitting. The drama is that the wave is only slightly off from what the standard model expects, yet the offset is stubborn. A plot of residuals, tiny deviations from a fitted curve, becomes the documentary's suspense line, because that is where hidden biases would reveal themselves, yet the size of the discrepancy depends on which standard model input you trust most. If the theory value shifts, the crack can widen or narrow. That dependence is not a weakness of the method. It is a reminder that the standard model prediction is a composite object with multiple sources of uncertainty. The same experimental number can look like a discovery or a lesson in hadronic physics, depending on how the theory ledger is balanced. This is where scientific method becomes visible under strain, because precision forces honesty. Every systematic uncertainty is interrogated, because a few parts per billion can decide the narrative. The question is not only what the central value is, but whether every known bias has been found and bounded. The culture of the field becomes part of the measurement, skeptical, redundant, and designed to survive disappointment. Experiments cross-check magnetic field maps, beam dynamics, and detector timing. The theory community cross-checks datasets, radiative corrections, and lattice systematics. Independent teams redo analyses with different assumptions, because agreement is meaningful only when it survives different paths. When the same answer emerges from rival methods, it carries a special weight, because it is harder for a shared mistake to hide. On the experimental side, the magnetic field must be uniform and known, and even tiny gradients can matter. The muon beam must be understood in phase space, because betatron oscillations and electric fields can shift the effective precession frequency. The detectors must stay linear and stable, because pile-up and gain drifts can mimic small shifts. Even the distribution of muon momenta in the ring, slightly broader or narrower than expected, can change how corrections are applied. On the theory side, radiative corrections to the E plus E minus data must be applied consistently, because the measured cross-sections include photon emission and detector acceptance effects. Combining datasets requires careful treatment of correlations, because different experiments share systematic sources. Lattice calculations require continuum extrapolations because the grid is not the world. Each of these steps is a potential place for optimism to creep in, so the community builds conservative error budgets and then tries to break them. The tension is productive because it is falsifiable, and because independent approaches can converge. If the discrepancy survives, it becomes a signpost to new physics. If it dissolves, it becomes a case study in how difficult it is to compute strong interaction effects with the needed precision. Either way, the process strengthens the infrastructure of precision physics, which will be needed for whatever anomaly comes next. Now translate the anomaly into candidate interactions, because the audience needs stakes. A new boson, a leptoquark, or a supersymmetric partner could sit in the loop. The key is that the new contribution must have the right sign and size, and it must be compatible with everything else we have measured. That compatibility is the hard part, because G-2 is not isolated. It is entangled with flavor, electroweak data, and collider limits. Any candidate must do two things at once, which is why the story feels like a trap. It must shift them enough, and it must evade decades of null searches. The Muon anomaly is not asking for a tiny tweak. It is asking for a coherent story that does not break other precision tests. The more you tune a coupling to help the Muon, the more you risk leaving fingerprints in rare decays or high-energy tails. A light new gauge boson, sometimes called a Z-prime, could couple preferentially to muons. In loop terms, it would add a new diagram that alters the magnetic moment, and the effect could be enhanced if the coupling is tailored. But such a boson would also show up in other processes, and those absences become constraints. It would affect neutrino trident production, muon pair spectra, or the running of couplings, so its hiding places are limited. Leptoquarks offer a different mechanism. They connect leptons to quarks, so their loops can involve heavy quarks and generate sizable contributions to AM. Yet they are also constrained by rare decays, by flavor-changing processes, and by direct production bounds at colliders. The same interaction that helps the muon can accidentally induce forbidden transitions, which is why model builders often invoke alignment to keep flavor violation under control. Supersymmetry, historically one of the most studied frameworks, can contribute through Muon, Neutrino and Neutrino chargino loops. Those contributions can naturally scale with the muon mass, and with tan beta in certain parameter regions. However, the LHC has pushed many superpartner masses upward, narrowing the space where the effect remains large. The remaining parameter space is not empty, but it is more structured, requiring careful choices of spectra and mixing. This is where CERN enters as a constraint machine, not just a discovery machine. LRP fixed electroweak couplings and Z properties with per-Miller precision. Those measurements were not flashy, but they were sharp, and they still define the boundaries of what new physics can do at the Z-pole. Precision line-shape scans turn the Z-boson into a ruler, and that ruler still measures the viability of new ideas. ELEPS measurements limit new light states that would change the Z-width, or distort its couplings. The invisible width still points to 3 active neutrinos, not more. That result is a quiet pillar of the standard model, because it tells us how many light, weakly interacting species couple to the Z. If additional light particles exist, they must be more hidden than a standard weak charge would allow. In archival footage, LRP looks almost serene, an underground ring where electrons and positrons met with exquisite control. Yet the data it produced are like a fingerprint database for electroweak physics. Any new particle light enough to be produced at the Z would have left a trace in the line shape, and it did not. That absence is not emptiness, it is a boundary condition that every muon-inspired model must respect. At the LHC, direct searches look for new particles that could generate the needed loop effects. Many models predict signatures in muon, tau, or missing energy channels. The LHC is a different kind of machine, not tuned for one resonance, but throwing enormous energy into the vacuum to see what falls out. In visuals, proton bunches become luminous bullets, and the detectors become layered cathedrals of silicon, scintillator, and steel. But the LHC has not produced a clear new resonance that explains G-2. Null results push viable models into corners with tuned couplings or heavier masses. The absence is not merely a lack of excitement, it is a quantitative statement that certain cross-sections and decay patterns are not present. Each new dataset redraws exclusion plots, shrinking the allowed islands where new physics can hide. That absence is not failure, it is information, and it deepens the mystery of hiding. If new physics exists, it is either subtle, heavy, or flavor selective. The muon anomaly, if real, would then be a rare case where the vacuum whispers even when the collider shouts and hears nothing back. It invites a thought-provoking question. What kind of theory prefers to show itself in loops but not in direct production? Now widen from G-2 to lepton universality, because universality is the Standard Model's central promise about generations. The W and Z should couple equally to E, M and T. The only differences should come from the lepton masses and from well-understood phase space effects. If that promise fails, it is not a small correction. It is a statement that the copies are not truly copies. Universality is never tested as a slogan, it is tested as ratios that cancel uncertainties. Compare decay rates where only the lepton flavor changes. Ratios are powerful because many messy hadronic factors and experimental efficiencies divide out, leaving a clean comparison of couplings. In the best cases, you are left with a number that theory predicts with tiny uncertainty, so any deviation has nowhere to hide. Start with mesons, because they are clean laboratories for weak couplings. Pions and kaons decay to Ln, and the ratios are predicted precisely. These decays are simple two-body processes, and the Standard Model prediction is controlled by the V-A structure of the weak interaction. The hadronic physics is compressed into a decay constant, and in ratios even that largely cancels. The helicity suppression makes P to N rare compared to P to min, and that rarity is itself a test. In the Standard Model, the pion is spinless, and angular momentum conservation forces the outgoing lepton to be in a helicity state that is disfavored for the electron. The suppression is proportional to the lepton mass squared, which makes the electron channel extremely sensitive to new scalar interactions. A tiny scalar contribution can compete with a heavily suppressed Standard Model amplitude, so the ratio becomes a high-gain amplifier. When you show this visually, the pion decay is almost minimalist. A single track and missing energy, a clean vertex, and then the statistical weight of millions of decays building a ratio. The surprise is that the rare channel is not just a curiosity, it is a magnifying glass for new currents. The audience can see how a simple counting experiment, repeated with care, becomes a probe of Lorentz structure. Kaon decays provide additional ratios, including K to N versus K to men and semileptonic modes. Small deviations can indicate new currents or scalar couplings. Because kaons involve a strange quark, they also probe different hadronic matrix elements and different sensitivity to possible flavor structures. Historically, kaon physics has repeatedly revealed deep principles, from parity violations implications to the discovery of CP violation. Semileptonic decays, where a kaon decays into a pion plus a lepton and a neutrino, add a complementary handle. The kinematic distributions and form factors can be measured, and the lepton flavor dependence can be isolated. Here again, the Standard Model makes precise predictions once the hadronic form factors are constrained. The shapes of the spectra, how events populate energy and angle, carry information beyond a single branching ratio. Move to W decays because they test the charged current directly at high energy. The branching fractions to En, min and Tn should match after mass effects. The W is heavy enough that the lepton masses are small corrections, so any persistent difference would be hard to explain away. In collider visuals, W events are defined by a single energetic lepton and a missing momentum vector, like an arrow pointing to an invisible neutrino. Move to Z decays, because they test neutral currents and were measured exquisitely at LEP. Z to E, E, MM and TCT should agree within tight bounds. The Z couplings are chiral, and LEP measured not only rates but as symmetries, which makes the constraints multidimensional. That multidimensionality matters, because new physics can hide in one observable while being exposed by another. Tau decays give a third angle, because the tau can decay to En or man with predictable ratios. Those ratios test whether the W treats M and E equally. The tau is heavy, so it opens many hadronic decay channels as well, and those channels can also be used to test universality through spectral functions. In visuals, tau events look like tiny fireworks, short tracks and displaced vertices, because the tau decays before it can travel far. Across these tests, the Standard Model mostly holds, which is why any deviation becomes dramatic. The pattern is consistent, but it is not perfectly quiet. Precision experiments often report tiny tensions that come and go as datasets improve, and the field has learned to treat them as clues, not conclusions. The deeper observation is that universality is not a single test, but a network, and a real effect should eventually appear coherently across that network. Introduce the idea that new physics could be generation-dependent, because that is the thematic link to copies. A new gauge boson could couple to muons more than electrons, Such a coupling pattern might be tied to a new symmetry that distinguishes lepton flavors, even if that symmetry is hidden at accessible energies. If so, the muon's heavier mass is not the only reason it stands out. Its charge under a hidden symmetry could be different. Leptoquarks could connect leptons to quarks in ways that violate naive universality. New scalars could alter helicity suppression and shift meson-decay ratios. In each case, the new interaction changes the effective operators in the low-energy theory, and the ratios move because the underlying Lorentz structure has changed. The ratios are therefore not just numbers, they are diagnostics, telling us whether nature prefers vector, axial, scalar, or tensor currents. If such interactions exist, they would reshape the flavor structure rather than just add particles. They would imply that generations are not redundant, but differentiated by hidden charges. That is a profound shift because the standard model currently treats generations as copies with different Yukawa numbers pasted on. The question becomes almost philosophical, but it remains testable. Are the Yukawas arbitrary, or are they shadows of a deeper organizing rule? Now connect to CERN constraints again, because models must survive both precision and production. A Z prime that couples to muons is constrained by dilepton spectra at the LHC. Even if it couples weakly, it can show up as a bump, or as a distortion in the high-mass tail, and those spectra are now measured with impressive reach. In the visuals, a smooth falling distribution becomes a canvas where a tiny excess would appear like a ripple. Leptoquarks are constrained by pair production searches and by rare decay measurements. Even when not seen, their allowed couplings are squeezed into narrow windows. The LHC can produce leptoquarks through QCD interactions, which makes the constraints relatively model-independent once the decay modes are specified. Each null result is a sculptor's chisel, carving away parameter space and forcing theories into more specific shapes. This is where the story's tension peaks, because the clues pull in opposite directions. The muon anomaly wants new effects, but colliders demand those effects be hidden. How do you make something influential enough to shift M, yet elusive enough to avoid direct detection and other precision bounds? That question is not rhetorical, because it guides what experiments should build next and what theorists should prioritize. So theorists build models with flavor alignment, loop suppression, or heavy mediators. Each fix explains one constraint but risks creating another problem elsewhere. A coupling pattern that helps G-2 might induce rare decays, or it might spoil electro-weak precision observables, or it might conflict with neutrino scattering data. The models become delicate machines, and the audience can sense the fragility. One new bound can snap an elegant idea. The deeper lesson is that the standard model is not easy to beat. It is over-constrained by decades of measurements, so any new ingredient must slip into the gaps without tearing the fabric. That is why the Muon anomaly, if it persists, would be so valuable. It would be a rare thread to pull. Pull it far enough, and you might unravel a hidden sector, or you might discover that the fabric itself was mismeasured. Now introduce the broader flavor puzzle explicitly, because it is the chapter's conceptual climax. The standard model contains Yukawa couplings that set masses, and it does not explain them. They are parameters we measure and insert like a codebook we did not write. In the equations, they look simple, but in meaning they are deep because they decide who is light, who is heavy, and who mixes with whom. The electron, muon, and tau masses differ by orders of magnitude, and the Yukawas encode that hierarchy. The numbers look patterned, yet they are inputs. The muon is not merely heavier, it is heavier by a factor that seems too specific to be random, and too unexplained to be satisfying. When you line up the masses on a logarithmic scale, the spacing looks like a clue, but the standard model offers no key. Quarks also show hierarchies and mixing described by the CKM matrix. Neutrinos show a different mixing pattern, described by the PMNS matrix. Mixing matrices are not decorative, they describe how weak interaction states are rotated relative to mass states, and that rotation has measurable consequences. In experiments, that rotation becomes oscillations, interference patterns, and CP violating asymmetries that can be plotted and compared. PMNS angles are large compared to CKM angles, and that contrast is a clue. It suggests that flavor is not a single simple mechanism across all fermions. Why do quarks mix only modestly while neutrinos mix so freely, and what symmetry or dynamic sets those patterns? The question points back to the opening theme. The standard model's copies may be hiding a deeper geometry of flavor. Historically, the very existence of generations emerged gradually. The muon was discovered in cosmic rays in the 1930s, and it puzzled physicists because it seemed like an electron that refused to fit into atomic physics. Later, the discovery of strange particles and then the charm quark revealed that repetition was not an accident, but a structural feature. Each new copy arrived as a surprise, and each surprise later became a pillar. 3 generations are required for CP violation in quarks, and CP violation is required for matter to win. Yet the standard model's CP violation seems too small. The CKM phase does produce CP violating effects, and those effects have been measured in kaon and B meson systems, but their magnitude appears insufficient for cosmology. The universe is not impressed by a phase that is mathematically real but cosmologically weak. State the cosmological stake plainly, because this is where the documentary's mystery becomes existential. The observed baryon asymmetry demands new sources of CP violation. The universe contains far more matter than antimatter, and that imbalance is not a minor detail. It is the reason galaxies, planets, and observers exist. When you look at deep field images filled with galaxies, you're looking at the consequence of a tiny early universe preference. The standard model has CP violation in the quark sector, but calculations indicate it cannot generate the observed matter excess. Something else likely contributed. The electroweak phase transition in the standard model is not strongly first order for the observed Higgs mass, which further weakens the case for standard model baryogenesis. Without a strong departure from equilibrium, CP violation has little leverage, and the asymmetry washes out. The lepton sector offers a plausible route, because neutrino mixing can include a CP violating phase. If neutrinos violate CP, early universe processes could amplify it. The same PMNS matrix that makes neutrinos oscillate could also encode asymmetries that matter when temperatures were high and reactions were rapid. Experiments that measure neutrino appearance probabilities are therefore not only measuring angles, they are testing whether the universe had a built-in bias. Leptogenesis is the leading narrative that connects these ideas, even if it remains unproven. Heavy neutrino decays could create a lepton asymmetry that sphalerons convert. Sphalerons are non-perturbative electroweak processes that violate baryon plus lepton number, and in the early universe, they can reshuffle asymmetries between sectors. The mechanism is subtle, but the moral is simple. Lepton physics can become cosmic history. That possibility ties the smallest masses to the largest outcome, and it keeps the 3-generation pattern central. The copies might exist because flavor is a cosmic engine, but if so, the Muons anomaly and universality tests become more than technical puzzles. They become hints about the machinery that set the initial conditions of everything. It is a striking inversion. A tiny frequency shift in a ring could be related indirectly to why anything exists to measure it. Now bring the chapter back to method, because the climax must feel earned, not asserted. An anomaly is not new physics until it survives independent scrutiny. The history of physics is filled with deviations that evaporated under better calibration, and with others that became revolutions only after relentless verification. The field therefore treats every tension like a suspect, questioned, cross-examined, and only slowly trusted. Theory predictions are audited through alternative inputs, improved lattice calculations, and new data on hadronic cross-sections. Experiments are audited through blind analyses and repeated calibrations. The goal is not to defend a favourite outcome, but to make it hard for any single mistake to survive. In that sense, the community builds an ecosystem of skepticism, because precision thrives on adversarial checking. The field is learning to treat precision like a collider, where the collision is between calculation and measurement. The winner is whichever survives every cross-check. Sometimes the collision reveals a new particle, and sometimes it reveals a missing term in an uncertainty budget, but either way it reveals truth. The most valuable outcome is not drama, but clarity, because clarity tells you what to build next. If G-2 converges to the standard model, the muon becomes a lesson in humility and hadronic complexity. If it persists, it becomes a doorway to a new sector. In both cases, the muon has already served as a guide, because it forced theorists and experimentalists to sharpen their tools. That sharpening matters because the next anomaly will demand the same discipline, and perhaps even more. If universality ratios stay exact, flavor-dependent models shrink and the mystery shifts toward neutrinos and yukawas. If small deviations grow, the generations gain hidden structure. Either outcome is informative, because it tells us whether the repetition of families is superficial or encoded in deeper symmetries. The documentary's mystery remains intact, but the map becomes sharper, with some paths closing and others opening. Now state the central riddle again, because the chapter must return to the documentary anchor. Why does nature repeat the lepton blueprint 3 times, then hide the reason? Is it merely an accident of how the Higgs couples, or is it a sign of a larger organizing principle that we have not yet named? When you hear 3 generations, you can almost hear a design choice, and the discomfort is that we do not know whose choice it was. The Muon anomaly and universality tests are not separate stories. They are 2 ways to interrogate the same pattern. They ask whether the copies are truly identical under forces. If the Muon is slightly out of step, it may be because it carries a faint imprint of new interactions that the electron does not feel. That imprint would be subtle by necessity, because the standard model's success leaves only narrow cracks where anything new can fit. The standard model has survived decades of assault, yet it already needed extension for neutrino mass. The question is whether the next extension is arriving through the muon. If the muon is a messenger, it is speaking in the language of parts per billion, and we have to learn to listen. Listening means patience, redundancy, and the willingness to accept either outcome, because nature is not obligated to be dramatic. End with a forward pull into the final chapter, keeping the tone mysterious and unresolved. The clues now point toward flavor as the organizing principle, not an accident. Next, we gather the leading hypotheses and the decisive future tests, because the field is close enough to feel the edge. If the copies are breadcrumbs, the trail is finally visible. We end where we began, with a familiar charge and a stranger echo. Nature repeats the electron as muon and tau, each paired with its own neutrino, 3 families that the standard model can list but not justify. It cannot explain why there are 3 generations, why masses span orders of magnitude, or why mixing angles settle on these particular values instead of others. On screen, the particle table looks like a neat ledger, yet the numbers feel like handwritten annotations in the margins. Neutrino oscillations already force new terms beyond the minimal model. The discovery that flavor changes in flight implies neutrinos have mass and mix, so the catalogue must be amended even before we understand the pattern. The Muon anomaly and universality tests ask whether more cracks align, because tiny loop corrections can amplify the influence of unseen particles. So why 3? One direction invokes flavor symmetries, continuous or discrete, that constrain Yukawas and mixing through hidden selection rules, like an invisible grammar shaping which couplings are allowed. Froggut, Nielsen mechanisms add heavy fields and a broken charge, generating hierarchies as powers of a small parameter, so the enormous spread in masses emerges from repeated suppression rather than arbitrary tuning. Grand unification links leptons and quarks, making generations part of a larger multiplus structure, though the mass pattern still resists prediction when the unified symmetry breaks. Extra dimensions can localize fermions differently, turning overlap with the Higgs into effective Yukawa hierarchies, and the visual becomes almost geometric, wave functions separated in an unseen direction. Compositeness proposes leptons are not elementary, and generations are excitations of deeper constituents, as if the muon and tau are heavier resonances of the same underlying object. Anthropic and landscape arguments treat parameters as environmental, explaining little but reframing what counts as an answer, and they leave a lingering question about what we should demand from explanation. Neutrino mass may be the key. Seesaw models introduce heavy sterile neutrinos, making light masses small and tying flavor to a high scale that could sit far beyond any collider. If neutrinos are Majorana, lepton number can be violated, and neutrinoless double beta decay becomes the decisive test, an ultra-rare nuclear transition that would reveal neutrinos as their own antiparticles. That same lepton number violation can power leptogenesis, where heavy neutrino decays create an asymmetry later converted into baryons, offering a route from microscopic flavor physics to the existence of galaxies. Cosmology keeps score. Relic neutrinos shape structure by free streaming, and their masses suppress clustering in ways surveys can measure, subtly smoothing the cosmic web on the larger scales. Early thermal history depends on which species existed when they decoupled, and whether hidden radiation altered expansion, so the universe itself becomes a detector with a memory. Next clues are experimental. Long baseline oscillation programs target CP violation and mass ordering, testing whether mixing encodes the cosmic bias between matter and antimatter. Neutrinoless double beta decay searches test Majorana mass directly, while improved Muon G2 and lepton flavor violation hunts look for loop-level fingerprints that the standard model cannot easily hide. Colliders keep probing for new mediators and for tau and muon couplings that would break universality, turning precision into a searchlight. The copies may be telling us the standard model is a low-energy shadow, and generations encode structure we have not decoded. The electron is the first page. The muon, tau, and neutrino are the margins where the universe keeps leaving hints, and the next measurement may finally show why the story repeats 3 times. We began with the electron, the quiet architect of chemistry, and found that its precision is not an accident but a measured constraint. Then, in cosmic ray tracks and collider debris, we met its heavier echoes, the muon and the tau, carrying the same charge, the same spin, the same electroweak rules, yet living on radically different scales of mass and time. The standard model records this repetition with elegant bookkeeping, 3 neat generations and lepton universality tests that mostly hold. But it offers no reason the ledger has 3 lines, or why the Yukawa numbers span orders of magnitude. The muon arrived as both a messenger and a microscope, its time-dilated journey to sea level proving relativity, and its tighter orbits in muonic atoms turning mass into resolution. In the muon's magnetic moment, that same mass becomes leverage, amplifying quantum loops where unknown particles could leave fingerprints, and where the G2 tension now sits, uncomfortable, persistent, and entangled with the hardest hadronic uncertainties. The tau, brief and violent, completes the charged lepton pattern while deepening the puzzle, because a third copy looks less like coincidence and more like design we do not yet understand. And then the neutrinos, everywhere, nearly invisible, broke the family rules outright, changing flavor as they travel, forcing mass into a theory that once forbade it. Oscillations turned 3 generations from a static taxonomy into a living quantum interference experiment, with mixing angles and phases that feel like a message written in probability. In cosmology, neutrinos are not footnotes but ingredients, decoupling seconds after the Big Bang, shaping expansion, nudging element formation, and smoothing structure through free streaming. Their tiny masses, measured indirectly on Earth and constrained across the sky, link particle physics to the growth of galaxies, as if the universe kept a record of the neutrino sector in its largest patterns. Yet the most consequential line remains missing, because we still do not know whether neutrinos are Dirac particles with hidden right-handed partners, or Majorana particles that erase the distinction between matter and antimatter. That single fact would decide whether lepton number is a true conservation law or a temporary accounting trick, and it would set the stakes for neutrinoless double beta decay as a decisive, world-changing observation. Ahead lie the hinge measurements that could turn the story: the neutrino mass ordering, the CP violating phase in long baseline beams, sharper universality tests, deeper searches for lepton flavor violation, and a muon G2 verdict that survives improved theory and data. Each of these is a different kind of question, but together they ask one larger thing: whether the lepton pattern is fundamental architecture, or the shadow of something deeper casting 3 similar silhouettes across our detectors and our cosmos. So why does reality repeat the electron 3 times? And why do 3 neutrinos haunt the universe like a background whisper we cannot quite hear? The most honest answer is that we do not yet know. But the repetition no longer looks like redundancy. It looks like a breadcrumb trail, placed where our best theory is strongest and therefore easiest to crack. If the standard model is a map, the generations are the places where the ink runs thin, where masses are inserted by hand, where flavor changes in flight, and where a small anomaly can become a doorway. The strange copies may be telling us that mass is not just a Higgs number, that lepton number may not be sacred, and that the early universe used the neutrino sector as a lever to tilt the balance between matter and antimatter. In that reframing, the question shifts from why 3 copies to what mechanism forces 3, and what cosmic bargain did those 3 help to strike. Because the universe did not merely make extra leptons, it used them, in the first seconds, in the shaping of radiation, in the cooling of plasma, and possibly in the asymmetry that let atoms survive at all. The electron makes the world familiar, but its heavier siblings make the world suspicious, as if nature is repeating a word we have not learned to translate. Somewhere between a Muon's precession a neutrino's phase, and a rare nucleus waiting to decay, there may be a single principle that turns 3 generations from a coincidence into an explanation. And if that principle exists, it will not just complete the standard model's missing page, it will rewrite our origin story, explaining how a universe that should have annihilated itself kept enough matter to become stars, planets, and us.